Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and the universe slowly stretches out around us like a sky that never quite runs out of room. Tonight, we're going to take a gentle walk through something that feels both familiar and impossibly distant. The home galaxy we've been orbiting inside since before humans ever looked up and wondered what those soft white smudges in the night sky might be. The Milky Way. A name that sounds almost cozy, like something you might pour into a glass before bed, but in reality it's a structure so vast that even our best maps still struggle to capture its full shape. And recently, a new set of eyes has begun quietly peering into its deeper corners, not with a dramatic fanfare or a cosmic drumroll, but with patient, careful observation. The James Webb Space Telescope has been sending back information that gently suggests something surprising. The Milky Way might be larger, deeper, and more complex than we've been telling ourselves for a very long time. Before we drift too far into that thought, let me ask you something simple and human. Where are you listening from right now? A bedroom? A couch? A quiet train ride? Or maybe a place where the lights are already dim and the world has begun to soften at the edges? And what time is it for you in this moment? In your own small corner of a galaxy that stretches hundreds of thousands of light years in every direction. If you find this space relaxing, or if you enjoy letting your thoughts wander slowly among stars and ideas, you're always welcome to like the video or subscribe. It helps this calm little corner reach others who might be looking for a gentle way to end their day. But for now, there's nowhere else you need to be. The universe is not in a hurry, and neither are we. So let's begin with something that seems simple on the surface. The Milky Way is our galaxy. That's the sentence most of us learned in school, written on a chalkboard or printed in a textbook beside a spiral diagram with a bright dot labelled, "You are here." It feels tidy, it feels manageable, a disk of stars, some arms curving outward, a glowing centre, and our solar system sitting politely off to one side like a guest who arrived early and isn't quite sure where to stand. But even that familiar picture hides a quiet problem. No one has ever taken a photograph of the Milky Way from the outside. Every image you've seen of our galaxy as a whole is an artist's interpretation, a careful guess based on years of measurements, motion tracking, and light analysis. We live inside the thing we're trying to map. It's a bit like trying to draw a forest while standing in the middle of it, surrounded by trees, mist, and shadows. For most of human history, the Milky Way was not even a galaxy. It was a pale, milky band across the night sky, something to build stories around. Ancient cultures saw it as a river, a path for spirits, a trail left by gods, or spilled light from some cosmic event long forgotten. It wasn't until the early 20th century that astronomers realized that this soft stripe of light was actually made up of billions of stars, and that our sun was just one among them. Even then, understanding its true size was a slow and careful process. Early astronomers tried to measure distances by observing how stars appeared to shift position as Earth moved around the sun. This method, called parallax, works beautifully for nearby stars, but as soon as you start looking deeper into the galaxy, those shifts become so tiny that they're nearly impossible to detect. The Milky Way, it turned out, was playing a very effective game of hide and seek. To make things even more complicated, our galaxy is filled with dust. Not the kind that settles on shelves, but fine and cosmic grains made of carbon, ice and silicates, drifting between stars. This dust absorbs and scatters visible light, creating dark patches and glowing clouds that block our view of what lies beyond. If you've ever tried to look through a foggy window at night, you have a good sense of what astronomers have been dealing with for decades. So for a long time, our maps of the Milky Way were built from what we could see directly, combined with what we could infer. We tracked how stars moved. We measured how gas clouds glowed in radio waves. We watched how clusters of stars formed and drifted. Piece by piece, a picture began to emerge. A spiral galaxy about 100,000 light-years across, with several major arms a central bulge, and a vast halo of faint stars surrounding it, like a quiet, invisible ocean. That model worked well. It explained the motion of stars, it fit the data we had. It gave us a sense of scale that was already so large it was hard to truly feel. 100,000 light years means that light, moving at the fastest speed anything can go, would take 100,000 years just to cross from one side of the galaxy to the other. Every time you blink, light could have travelled around the Earth 7 times, and yet in galactic terms that's barely a step. Then, quietly, without much ceremony, James Webb opened its eye. The James Webb Space Telescope is not a traditional telescope in the way people often imagine one. It doesn't sit in a dome on a mountaintop. It doesn't point a glass lens at the sky and collect visible light. Instead, it floats far from Earth, nearly 1 million miles away, at a point in space where the gravitational pull of Earth and the Sun balance just enough to let it hover in a stable position. From there, it looks outward and inward, not with human eyes, but with instruments tuned to infrared light. Infrared is the kind of light we feel as heat. It's what lets you see warm shapes in a thermal camera, and in space, it has a special advantage. Infrared light can pass through dust clouds that block visible light. Where traditional telescopes see darkness, Webb sees structure. Where older instruments see a blank patch of sky, Webb sees stars being born, galaxies forming, and distant objects glowing faintly in the background. When Webb began observing regions of the Milky Way, astronomers weren't expecting a dramatic rewrite of the galaxy's size. They were looking for details, star formation, the chemistry of nebulae, the structure of the galactic center. But as data accumulated, patterns started to appear that didn't quite fit the neat, familiar model. In some directions, Webb detected stars much farther out than expected. Not just a few scattered stragglers, but extended populations of faint, distant stars that suggested the galaxy's disk and halo might stretch farther into space than previous measurements indicated. These weren't bright, obvious objects. They were subtle, quiet points of light, the kind that only show up when you look with patience and the right kind of vision. One of the challenges in measuring a galaxy's size is deciding where it actually ends. There's no clear edge, no galactic fence marking the boundary between Milky Way and not Milky Way. Instead, the density of stars slowly thins out. The bright spiral arms fade into scattered clusters. The disk blends into a halo of old, dim stars that orbit far from the center. Beyond that, there's intergalactic space, where the distances between stars grow so large that the concept of a galaxy starts to feel more like a suggestion than a solid shape. Webb's ability to detect extremely faint infrared signals has made it possible to see parts of this halo in greater detail than ever before. And what it's revealing is that the Milky Way's influence, its gravitational reach, and its population of stars extends farther than we used to think. To understand why this matters, it helps to imagine the galaxy not as a flat picture, but as a three-dimensional structure. There's the thin disk where most of the stars, gas and dust live. That's where the spiral arms are, where new stars form, and where our solar system happens to be. Then there's the thick disk, a puffier, older layer of stars that sits above and below the thin one. And surrounding all of that is the halo, a vast, roughly spherical region filled with ancient stars and dark matter. Dark matter is another quiet player in this story. It doesn't emit light. It doesn't absorb light. We can't see it directly at all, but we can see its effects. Stars in the outer parts of the galaxy move faster than they should if only visible matter were present. Something else is adding extra gravity, holding the galaxy together like an invisible framework. That something is dark matter, and it likely makes up most of the galaxy's mass. When Webb observes the outer regions of the Milky Way, it's not just looking at stars, it's helping astronomers trace the shape of this hidden structure. The farther out stars are found to orbit in stable patterns, the more we learn about how far the galaxy's gravitational influence truly extends. In some recent studies, astronomers using Webb's data alongside other observatories have suggested that the Milky Way's stellar halo could stretch hundreds of thousands of light years from the centre. That doesn't mean it's packed with stars all the way out there. It means that the galaxy's presence, its faint, quiet population of ancient stars, and its dark matter envelope reaches much farther into space than the bright, familiar spiral arms. It's a bit like realising that the cosy, well-lit rooms of a house are surrounded by a sprawling, dimly lit yard that you never noticed before. The house is still the part where most of the activity happens, but the property line is much farther out than you assumed. There's another layer to this story, and it comes from looking not just at where stars are, but how they move. The Milky Way is not alone in space. It's surrounded by dozens of smaller satellite galaxies, like the Large and Small Magellanic Clouds, along with many faint dwarf galaxies that are so dim they're hard to detect at all. These smaller systems orbit the Milky Way, drawn in by its gravity, sometimes being stretched and torn apart in the process. Webb's observations of stars in the outskirts of the galaxy have helped astronomers identify streams of stars that don't quite fit the main rotation of the Milky Way. These streams are the remains of smaller galaxies that wandered too close and were gradually pulled apart, their stars now forming long, faint trails that wrap around our galaxy like cosmic ribbons. The presence of these streams tells us that the Milky Way has grown over time by absorbing other galaxies. It's not a static object. It's a structure built through countless slow encounters, mergers and gravitational dances that have been playing out for billions of years. And this growth process contributes to the galaxy's true scale. The more material it has absorbed, the farther its halo extends. The more dark matter it gathers, the larger its gravitational footprint becomes. Webb's ability to see faint, distant stars makes these ancient interactions easier to trace, revealing a history that is written not in words, but in motion and light. Now, it's worth pausing for a moment to think about where we are in all of this. Our solar system sits about 26,000 light-years from the centre of the galaxy. That's far enough out that we're not in the crowded, energetic core, but still well within the bright, active disk. We orbit the centre once every 230 million years or so. That means that since the first dinosaurs appeared on Earth, the Sun has gone around the galaxy just once. From our position, we look out through layers of stars, gas and dust in almost every direction. The night sky we see is shaped by this placement. We see the Milky Way as a band because we're looking along the plane of the disk, where stars are most densely packed. When we look up or down, away from that plane, the sky becomes darker and emptier because we're looking out of the disk and into the halo. Webb's discoveries gently remind us that even in those darker directions, the galaxy doesn't simply stop. It fades, it stretches, it becomes quieter, but it continues. This idea of a galaxy without a sharp edge can feel a little unsettling. We like boundaries. We like knowing where things begin and end. But the universe doesn't always cooperate with that preference. Structures in space often blur into one another. Galaxies interact. Halos overlap. Gravity weaves everything into a kind of slow, continuous network. In a way, learning that the Milky Way is larger than we thought doesn't make it more distant. It makes it more present. It means that the space around us, the region we move through every second as Earth spins and orbits the Sun, is part of a much bigger system than the neat diagram suggested. We're not just inside a disk of stars. We're inside a vast, layered structure that reaches far into the dark between galaxies. And this is only part of what Webb is beginning to show. Its observations are still accumulating. New data sets are being analysed. Patterns are being checked and rechecked. Science moves slowly here, not because it's uncertain, but because it's careful. Each claim about the galaxy's size and structure has to be supported by multiple lines of evidence from different instruments and methods. As that work continues, our picture of the Milky Way will keep shifting, not in sudden leaps, but in small, steady adjustments. A little farther here, a little more mass there. A faint stream of stars added to the map. A new region of the halo traced in more detail. If you let that idea settle for a moment, it has a gentle kind of effect. The galaxy is not a fixed backdrop. It's an evolving environment. It's something we're moving through, something that's changing around us on timescales far longer than a human life, but not so long that they're meaningless. And as we follow this trail of thought, it naturally leads to another question that doesn't rush for an answer. If the Milky Way is larger than we believed, if its structure is more layered and extended, then what does that mean for how we understand our place within it, and how we compare our home galaxy to the countless others scattered across the universe? For a long time, the Milky Way felt like something we had more or less figured out, not in the sense that every star had been counted or every cloud of gas neatly catalogued, but in the comfortable way you might feel about a familiar neighbourhood. You know the main roads, you recognise the landmarks, you have a general sense of where things are, even if you've never explored every side street. That was the relationship astronomers had with our galaxy for much of the last century. There was a working model, a shared mental map, and a quiet confidence that while details would change, the overall shape and scale were reasonably well understood. If you open a textbook from just a couple of decades ago, you'll likely find a familiar picture. The Milky Way is drawn as a barred spiral galaxy, a flat disk of stars with several curved arms wrapping around a bright central bulge. Our Sun is placed somewhere between two of those arms, about halfway out from the centre, marked with a small, humble dot. Around the disk is a faint spherical halo of old stars and globular clusters, and beyond that, a vast invisible envelope of dark matter that holds everything together. It's a clean image, it fits nicely on a page, it's easy to remember, and for a long time, it worked well enough. The roots of this picture go back to a period when astronomers were just beginning to realise the true scale of the universe. In the early 1900s, there was still debate about whether the Milky Way was the entire universe, or just one island of stars among many. Some thought that the faint, fuzzy spirals seen through telescopes were clouds of gas within our own galaxy. Others suspected they were separate galaxies far beyond it. That question was settled in 1924, when Edwin Hubble measured the distance to the Andromeda Nebula and showed that it lay far outside the Milky Way. Suddenly, our galaxy went from being the whole universe to being one among billions. But even with that revelation, understanding the Milky Way itself remained a challenge, because we were still stuck inside it, trying to measure it from within. One of the first big steps toward mapping our galaxy came from studying star clusters. Globular clusters, in particular, turned out to be useful guides. These are dense, spherical collections of very old stars that orbit the centre of the galaxy, mostly in the halo. By measuring their distances and plotting their positions, astronomers noticed that they weren't evenly distributed around the Sun. Instead, they seemed to cluster around a point far away in the direction of the constellation Sagittarius. That point, it turned out, marked the true centre of the Milky Way. This discovery, made in the 1990s by Harlow Shapley, shifted our sense of place in a profound way. We were no longer near the centre of the galaxy. We were off to the side, one star system among many, orbiting a distant, crowded core. The Milky Way became something larger, more structured, and less centred on us. As telescopes improved, astronomers began to identify the spiral arms of the galaxy by tracing regions of star formation. Young, massive stars shine brightly and don't live very long, so they tend to stay close to the gas clouds where they were born. By mapping these bright stars and the glowing hydrogen gas around them, scientists could sketch out the rough pattern of the Milky Way's arms. Over time, a consensus emerged. The galaxy appeared to have 4 major spiral arms, along with a few smaller spurs. The disk was about 100,000 light-years across. The central bulge was thick with stars, and a long bar of stars stretched across the centre, helping to funnel gas inward and fuel new star formation. This model was supported by observations across different wavelengths. Radio telescopes mapped clouds of hydrogen gas. Infrared telescopes peered through dust to see stars near the galactic centre. Optical telescopes filled in the nearby regions with detailed star catalogues. Each piece of the electromagnetic spectrum added another layer to the picture, like stacking transparent maps on top of one another. And yet, even as this image solidified, there was always an awareness that it was incomplete. One of the biggest limitations was distance measurement. Knowing how far away something is in space is surprisingly difficult. For nearby stars, astronomers use parallax, the apparent shift in a star's position as Earth moves around the Sun. This method is precise, but it only works reliably out to a few thousand light-years. Beyond that, the shifts become too small to detect with traditional instruments. For more distant stars, astronomers rely on standard candles, objects whose intrinsic brightness is known. By comparing how bright they appear to how bright they should be, you can calculate their distance. Certain types of variable stars, like Cepheid variables, are especially useful for this purpose. They pulse in brightness in a way that's directly related to how luminous they are. But even these methods come with uncertainties. Dust can dim light. Crowded regions can make stars blend together. Different types of stars can be mistaken for one another. Each measurement carries a margin of error, and when you stack thousands or millions of these measurements together, those small uncertainties can add up. So the Milky Way we thought we knew was always a bit fuzzy around the edges. Another challenge came from the fact that the galaxy is not static. Stars move, gas flows, spiral arms shift and change over time. The Milky Way is not a frozen snapshot. It's more like a slow-motion scene, where everything is drifting, orbiting and evolving on timescales that stretch far beyond a human lifetime. This dynamic nature means that any map of the galaxy is a momentary approximation. It captures where things are now, not where they were millions of years ago, or where they'll be millions of years from now. And because light takes time to travel, even now is a relative term. When we look at a star 10,000 light-years away, we're seeing it as it was 10,000 years in the past. So in a very real sense, our picture of the Milky Way has always been a patchwork of different eras stitched together into a single image. Despite these complications, the basic structure seemed solid. The disk, the arms, the bulge, the halo. These elements appeared again and again in observations and models. Astronomers could simulate how such a galaxy would form and evolve, and the results matched what we saw in the sky. There was comfort in that consistency. It suggested that we had a handle on the big picture, even if the details were still being filled in. One of the most powerful tools in building this picture was the study of stellar motion. By measuring how stars move through space, astronomers can infer the gravitational forces acting on them. This, in turn, reveals how a mass is distributed throughout the galaxy. When these measurements were first made, they led to a surprising conclusion. Stars in the outer parts of the Milky Way were moving faster than expected. According to Newton's laws, if most of the galaxy's mass were concentrated in the visible stars and gas, then stars farther out should orbit more slowly. But they didn't. The only way to explain this was to assume that there was a large amount of unseen mass extending far beyond the visible disk. This was one of the key pieces of evidence for dark matter. It suggested that the Milky Way is embedded in a massive invisible halo that dominates its overall mass and shapes its motion. This realization expanded the galaxy in a conceptual sense, even if the visible stars still seem confined to a relatively neat disk. The true Milky Way, it turned out, was not just what we could see. It was also what we could feel through gravity. As surveys grew more comprehensive, astronomers began to discover faint dwarf galaxies orbiting the Milky Way. Some were found because they contained small numbers of stars that stood out against the background. Others were detected through subtle patterns in star motion. Each new satellite galaxy added another layer to our understanding of the Milky Way's environment. These small companions were not just decorative, they were evidence of the galaxy's history. The Milky Way, like many large galaxies, has grown by absorbing smaller ones. Over billions of years, it has pulled in and torn apart dwarf galaxies, scattering their stars into long streams that now arc through the halo. By mapping these streams, astronomers could reconstruct parts of the galaxy's past, identifying where and when it had interacted with other systems. This process revealed the Milky Way as something more like a collector than a solitary island, shaped by a series of slow, gravitational encounters. Even with all this, the general scale of the galaxy seemed settled. About 100,000 light-years across for the disk, a halo extending perhaps twice that. A total mass dominated by dark matter, roughly 1 trillion times the mass of the Sun. These numbers appeared in papers, lectures, and public science books. They became part of the shared language of astronomy. If you asked someone how big the Milky Way was, you'd likely get an answer in that range. But those figures were always based on the best available data at the time, and science, by its nature, is provisional. It builds models that work until new evidence suggests they need revision. One area where uncertainty lingered was the outer regions of the galaxy. The halo, in particular, is faint and difficult to study. Its stars are old and dim. They're spread thinly across vast volumes of space. Detecting them requires sensitive instruments and careful analysis to separate them from background objects in distant galaxies. For a long time, most surveys focused on the brighter, denser parts of the galaxy. The disk and the nearby halo were relatively well mapped. The far halo remained largely unexplored, a region where data points were sparse and interpretations tentative. This meant that our sense of where the Milky Way ended was partly a matter of convenience. We defined boundaries based on where our observations dropped off, not necessarily where the galaxy itself truly faded into the cosmic background. There was also the issue of perspective. Because we are inside the disk, our view is heavily biased. We see the galaxy edge on when we look along the plane, and face on only in small patches when we look up or down. This makes it difficult to get a global sense of shape and extent. Astronomers have developed clever methods to compensate for this, using star counts, motion data, and models of galactic structure. But no method is perfect. Each relies on assumptions, and those assumptions can subtly influence the results. For example, when estimating the total number of stars in the Milky Way, scientists have to extrapolate from the regions they can see to the regions they can't. If the density of stars in the far halo is higher or lower than expected, the total count changes. The same goes for mass estimates based on how fast stars and gas are moving at large distances from the centre. These uncertainties don't mean the old model was wrong, they mean it was a best guess based on incomplete information. Another piece of the puzzle came from comparing the Milky Way to other galaxies. Astronomers observed spiral galaxies of similar size and brightness in the local universe, and used them as points of reference. If those galaxies had certain properties, it was reasonable to assume the Milky Way might be similar. This comparative approach helped fill in gaps, but it also introduced its own assumptions. Our galaxy could be typical, or it could be somewhat unusual. Without an external view, it's hard to be sure. Over time, more advanced surveys began to chip away at these uncertainties. Space missions like Gaia started measuring the positions and motions of over 1 billion stars with unprecedented precision. This created a detailed 3-dimensional map of the nearby galaxy, revealing streams, clusters, and subtle structures that had never been seen before. Gaia showed that the Milky Way's disk is not perfectly flat. It's warped and rippled, like a vinyl record that's been left in the sun too long. It revealed that the galaxy has experienced recent interactions with satellite galaxies, leaving waves of motion that are still propagating through the stars. These findings added texture and complexity to the picture. The Milky Way was no longer just a neat spiral. It was a dynamic, slightly messy system, shaped by ongoing gravitational relationships. And still, the question of scale remained open. How far out do those faint halo stars really go? How large is the dark matter envelope? Where does the galaxy's gravitational influence truly give way to the wider cosmic web? Before Webb, answers to these questions were based on indirect evidence and limited observations. Astronomers could track the motion of satellite galaxies and use that to estimate the mass and extent of the dark matter halo. They could search for faint stars in deep surveys, but those surveys covered only small patches of sky. The picture that emerged was something like a soft-edged sphere surrounding the bright disk, extending perhaps 200,000 or 300,000 light-years from the centre. Beyond that, the Milky Way's presence would blend into the gravitational fields of neighbouring galaxies, particularly Andromeda, which is on a slow collision course with us. This idea of overlapping halos hinted at a future where the two galaxies would merge, but it also suggested that the boundaries of each galaxy were already less distinct than a simple diagram might imply. So when people spoke of the Milky Way's size, they were often referring to the visible disk. The halo was acknowledged, but it lived in a small abstract part of the conversation, something mentioned in passing rather than pictured in detail. All of this formed the background against which James Webb began its work. Astronomers were not expecting a complete overhaul. They were expecting refinement, better resolution, clearer images, more precise measurements. What they found instead was a quiet reminder that even the most familiar cosmic structures can still hold surprises, especially in the places where our previous tools couldn't quite reach. The Milky Way we thought we knew was not a mistake. It was a stepping stone, a version of the truth that fit the evidence available at the time, and like all good scientific models, it was designed to be replaced when better data came along. As Webb's observations started to fill in those faint, distant regions, the edges of the galaxy began to look less like a gentle fade and more like a complex, extended structure, with its own patterns and histories. The halo appeared richer, the outskirts more populated, the gravitational reach more pronounced. This doesn't mean that the galaxy suddenly grew overnight. It means our awareness of it did. At first glance, measuring a galaxy sounds like the kind of problem that should come with a very large ruler and a very patient scientist. You point, you measure, you write down a number, and you move on. But in practice, it's one of the most complicated tasks in astronomy, not because the math is especially tricky, but because of where we are standing while we try to do it. Imagine trying to map the size of a city while walking through its streets with a thick fog hanging in the air. You can see the buildings right around you. You can hear traffic in the distance. You might even catch glimpses of a skyline far away. But you never get the luxury of stepping back and seeing the whole thing at once. That's essentially the situation we're in with the Milky Way. We are residents, not visitors. We live inside the structure we're trying to measure. The most basic problem starts with distance. In everyday life, distance is intuitive. You walk from one place to another, you drive across town, you look at a map and get a sense of how far something is. In space, that intuition quickly falls apart. Even the nearest star beyond the sun is more than 4 light-years away. That's about 40 trillion kilometers. Numbers that large stop feeling like measurements and start feeling like abstract concepts. Astronomers have developed clever ways to measure distance, but each method works only within a certain range and comes with its own set of assumptions. The first and most direct technique is parallax. This is the same effect you notice if you hold your thumb up and look at it with one eye closed, then switch eyes. Your thumb seems to shift position against the background. That shift depends on how close your thumb is to your face. In astronomy, the idea is similar. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring that tiny shift and knowing the size of Earth's orbit, astronomers can calculate the star's distance using simple geometry. The problem is that this effect becomes incredibly small very quickly. Even for stars that are relatively close by in galactic terms, the shift is less than the width of a human hair seen from several kilometers away. Measuring it requires extremely precise instruments, and even then, parallax only works reliably for stars within a few thousand light-years. That covers our local neighbourhood, but the Milky Way is tens of thousands of light-years across. For anything beyond the reach of parallax, astronomers have to switch to indirect methods. One of the most important of these involves something called standard candles. A standard candle is an object in space whose true brightness is known. If you know how bright something really is, and you measure how bright it appears to be from Earth, you can calculate how far away it must be. Light spreads out as it travels, so distant objects look dimmer. Certain types of stars are especially useful for this. Cepheid variable stars, for example, pulse in brightness in a regular pattern. The period of their pulsation is directly related to their true luminosity. Measure how fast they brighten and dim, and you can determine how much light they're actually putting out. Another kind of standard candle is a type Ia supernova, a specific type of stellar explosion that reaches a consistent peak brightness. These are so bright they can be seen in other galaxies, making them useful for measuring distances on a much larger scale. But inside the Milky Way, even standard candles have their limitations. Dust gets in the way. Cosmic dust absorbs and scatters light, making stars appear dimmer and sometimes redder than they really are. If you don't account for that correctly, you can underestimate how bright a star truly is and overestimate how far away it must be. And dust is not evenly distributed. It clumps into clouds, filaments, and thick bands, especially along the plane of the galaxy. That means some lines of sight are relatively clear, while others are heavily obscured. Two stars at the same distance can look very different depending on how much dust lies between them and us. So every distance measurement becomes a small puzzle. How much of the dimness is due to distance, and how much is due to dust? Astronomers build models of dust distribution to correct for this, but those models are based on observations that are, themselves, affected by dust. It's a bit like trying to map fog density while standing in the fog. Then there's the problem of crowding. The Milky Way is dense, especially toward the centre. In some regions, there are so many stars packed into a small area of sky that they blur together. A telescope might see what looks like a single bright spot, but that light could actually be coming from dozens or hundreds of stars overlapping in the image. Separating those stars requires high resolution and careful data processing. Even with modern instruments, it's not always possible to disentangle every individual source, particularly in the most crowded regions of the galactic core. All of this makes it hard to create a clean three-dimensional map. Instead of a crisp, clear picture, astronomers often work with layers of probability. This star is likely at this distance within a certain margin of error. That cluster probably lies in this region of the arm, but it could be a little closer or farther than we think. When you scale that up to millions or billions of stars, the uncertainties start to shape the overall model of the galaxy's size and structure. Another layer of complexity comes from motion. Nothing in the Milky Way is standing still. Stars orbit the centre of the galaxy. Gas clouds swirl and collapse. Satellite galaxies drift around us, sometimes passing close enough to disturb the disk. By measuring how stars move, astronomers can learn a lot about the galaxy's mass and shape. This is done through something called spectroscopy, which involves splitting a star's light into its component colours. The exact pattern of those colours can reveal how fast the star is moving toward or away from us, thanks to the Doppler effect. If a star is moving toward us, its light is shifted slightly toward the blue end of the spectrum. If it's moving away, the light is shifted toward the red. By measuring this shift, astronomers can calculate the star's radial velocity, its speed along our line of sight. Combine that with measurements of a star's position and proper motion, its movement across the sky, and you can build up a three-dimensional picture of its trajectory through space. This is incredibly powerful, but it's also data-heavy and sensitive to error. Small mistakes in velocity measurements can lead to big differences in inferred orbits, especially over long timescales. When astronomers look at the outer parts of the Milky Way, they often rely on the motion of stars and satellite galaxies to estimate how much mass lies inside their orbits. This is similar to how you can estimate the mass of the Earth by measuring the orbit of the Moon. The faster something is moving in orbit, the more mass there must be inside that orbit to hold it in place. So if a dwarf galaxy is zipping around the Milky Way at high speed far from the centre, that suggests there's a lot of mass extending out to that distance, even if we can't see it. This method has been one of the main ways astronomers have estimated the size of the Milky Way's dark matter halo. But again, it depends on assumptions. You have to assume that the object you're measuring is in a stable orbit, and that you understand the forces acting on it. If a satellite galaxy is in the middle of being torn apart, or if it recently passed close to another massive object, its motion might not reflect the smooth, underlying gravitational field. So even gravity, which feels so reliable in everyday life, becomes a subtle and nuanced tool when you're dealing with structures that span hundreds of thousands of light years. There's also the issue of defining what size actually means for a galaxy. When we say the Milky Way is a certain number of light years across, what exactly are we measuring? Are we talking about the bright disk of stars, the faint halo of old stars, the invisible dark matter envelope, the region where the galaxy's gravity dominates over its neighbours? Each of these has a different boundary, and none of them have a sharp edge. The disk fades gradually. The halo thins out slowly. The dark matter extends far beyond the last visible star, blending into the dark matter halos of other galaxies. The gravitational influence of the Milky Way overlaps with that of Andromeda and other nearby systems, so any number you attach to the galaxy's size is to some extent a choice. It reflects a definition rather than an absolute physical wall in space. This is one reason why different sources sometimes give slightly different figures for the size and mass of the Milky Way. They may be measuring different components, or using different criteria for where the galaxy ends. Another complication comes from time itself. Because light takes time to travel, we never see the galaxy as it is right now. We see nearby stars as they were a few years ago. We see the centre of the galaxy as it was 26,000 years ago. We see distant halo stars as they were hundreds of thousands of years ago. For most practical purposes, this doesn't matter. The galaxy doesn't change dramatically on those timescales. But when you're trying to build a precise model, it means that your map is always a collage of different moments in the past. It's a bit like trying to make a family portrait using photos taken over several decades. The overall shape of the family is there, but the details reflect different stages of life, different expressions, different moments frozen in time. Then there's the problem of background confusion. When you look out toward the edge of the Milky Way, you're not just seeing our galaxy, you're also seeing distant galaxies far beyond it. Some of the faint points of light in deep surveys are not stars in the Milky Way at all. They're entire galaxies, millions or billions of light years away. Distinguishing between a very distant galaxy and a very faint nearby star can be surprisingly difficult. Both can appear as small, dim smudges of light. Astronomers use colour, motion, and spectral signatures to tell them apart, but those methods require high-quality data and careful analysis. Misidentifying background galaxies as halo stars or vice versa can skew estimates of how many stars the Milky Way has in its outer regions, and therefore how far it extends. All of this adds up to a situation where every measurement is part of a larger web of inference. Astronomers don't just measure one thing and declare the galaxy's size. They combine data from multiple sources across different wavelengths, using different methods, and then build models that best fit all of that information. Those models are tested, revised, and sometimes replaced as new data comes in. This is where new instruments make such a difference. A telescope that can see in a new part of the spectrum, or with higher sensitivity, can break through some of the old limitations. It can reduce uncertainties, reveal hidden structures, and challenge assumptions that were built into earlier models. James Webb does exactly this by operating primarily in the infrared. Because infrared light can pass through dust more easily than visible light, Webb can see stars and structures that were previously obscured. It can peer into dense regions near the galactic centre and into dusty areas of the disk and halo that older telescopes struggle to penetrate. It can also detect extremely faint sources, pushing the boundary of what counts as visible in the Milky Way. This makes it possible to identify stars in the far reaches of the halo and to study the distribution of faint low-mass stars that make up a large fraction of the galaxy's population. By combining Webb's data with information from missions like Gaia, which excels at measuring positions and motions, astronomers can create much more detailed three-dimensional maps. They can trace not just where stars are, but how they move and how they relate to the galaxy's overall structure. This is beginning to turn the Milky Way from a rough sketch into something closer to a living atlas, a dynamic model that shows not just static features, but flows, streams, and subtle patterns of motion. Still, even with these advances, the fundamental challenge remains. We are inside the system. We cannot step outside and take a single, clean photograph. We have to infer the whole from the parts, and those parts are always filtered through distance, dust, motion, and time. In a way, that makes the process more human. It's not about finding a final perfect answer. It's about gradually refining our understanding, filling in gaps, and being willing to adjust our picture as new information arrives. So when you hear that the Milky Way might be larger than we thought, what that really means is that our methods have improved enough to reach a little farther into the darkness. We're seeing stars that were always there, but were previously hidden or too faint to detect. We're tracing gravitational influences that were always shaping the galaxy, but were hard to map with older tools. The galaxy hasn't changed, our view of it has. If measuring our own galaxy is this complex, this layered with uncertainty and interpretation, what does that say about how we understand our place within it, and how our own perspective shapes the cosmic stories we tell? Somewhere between the first time a human looked up at the night sky and the moment you settled into this very second, a quiet assumption has followed us along like a shadow. We tend to believe that what we see, or at least what we can eventually measure, is a fair representation of what is truly there. The world looks a certain size, the sky feels a certain distance away, and the universe, for all its mystery, seems like something that can be gradually boxed into diagrams, numbers, and tidy explanations. But when it comes to something as enormous as a galaxy, that assumption begins to soften at the edges. The Milky Way is not just large in the way a mountain is large or an ocean is wide. It is large in a way that stretches the very idea of scale. It operates in units that have no natural place in everyday life. Light years, millions of stars, billions of years. These are not quantities we can directly experience. They are ideas we learn to handle through comparison, metaphor, and careful abstraction. And that is where human perspective quietly becomes part of the story. Our senses evolved to help us survive on a planet that is 8,000 miles across, orbiting a star that is one among many. We are very good at judging distances across a room, spotting movement in a field, or noticing subtle changes in light and sound. We are not naturally equipped to intuit the size of a structure that could swallow our entire solar system and never notice. So when astronomers talk about the scale of the Milky Way, they are not just dealing with instruments and data, they are also dealing with the challenge of translating something fundamentally inhuman in size into something the human mind can grasp. One way this shows up is in how we visualize the galaxy. Most people picture it as a flat spiral, like a glowing pinwheel floating in space. It's a useful image. It captures the idea of arms, a center, and a disk. But it also flattens something that is actually layered, thick, and three-dimensional into something that feels almost two-dimensional. The Milky Way's disk is not a thin sheet. It has depth. It has structure above and below the plane where most of the stars and gas reside. The halo extends far beyond that, wrapping the whole system in a faint spherical envelope. Dark matter stretches even farther, shaping the motions of everything within it. When we draw the galaxy on a page or a screen, we compress all of that into a symbol, and symbols by their nature leave things out. There's another subtler effect of perspective that comes from our position inside the galaxy. We are not neutral observers floating in empty space. We are embedded in a specific region, moving along a specific orbit, looking out through specific layers of stars, gas and dust. This means that the Milky Way does not present itself to us as a neat object with a clear outline. It presents itself as a sky full of points of light, streaked with a glowing band and punctuated by dark patches. Everything we know about the galaxy's shape and size has to be inferred from that internal view. Imagine trying to understand the shape of a city by standing on a single street corner and watching cars go by. You might notice that traffic flows in certain directions. You might see tall buildings in one area and shorter ones in another. Over time, you could build a mental map of where the downtown is, where the suburbs begin, and how the roads connect. But there would always be parts of the city you couldn't see directly. You would have to rely on second-hand information, indirect clues, and educated guesses. That's essentially how we study the Milky Way. We look at how stars move. We measure how light is absorbed and emitted. We trace the paths of gas clouds and satellite galaxies. From these pieces, we build a model of the whole, and just like any model, it reflects not only the thing being modelled, but also the perspective and limitations of the one doing the modelling. There's a psychological aspect to this as well. Humans are very good at thinking in relative terms. We understand big and small by comparing one thing to another. A house is big compared to a person. A mountain is big compared to a house. The Earth is big compared to a mountain. But when you get to the scale of a galaxy, those comparisons start to break down. The Earth is about 8 light minutes from the Sun. The Sun is about 4 light years from the nearest star. The Milky Way is about 100,000 light years across in its bright disk, and much larger when you include the halo. Each step up in that ladder of scale is not just an increase. It's a leap into a different category of size, and our intuition doesn't scale smoothly across those categories. This is why descriptions of the galaxy often rely on analogies. You might hear that if the solar system were the size of a coin, the Milky Way would be the size of a continent, or that if the Sun were a grain of sand, the nearest star would be miles away. These comparisons are helpful, but they are also reminders of how far removed the real numbers are from our everyday experience. Another limit of human perspective comes from time. We tend to think in years, decades, maybe centuries. History stretches back a few thousand years in our collective memory. But the Milky Way is billions of years old. It has been forming stars, absorbing smaller galaxies, and reshaping itself since long before the Earth existed. When we observe the galaxy, we are seeing it in a particular moment of its life. But that moment is just a thin slice of a much longer story. Even the light we see is a message from the past. When you look at a star in the night sky, you're not seeing it as it is right now. You're seeing it as it was when the light left it. For stars across the galaxy, that can mean tens of thousands of years ago. For distant galaxies, it can mean millions or billions of years ago. So the Milky Way, as we observe it, is a mosaic of different times layered on top of each other. Nearby stars are seen in the recent past. Distant halo stars are seen further back in time. The centre of the galaxy, 26,000 light years away, is seen as it was when humans were just beginning to paint on cave walls. This time layering adds another level of complexity to our perspective. We are not just inside the galaxy, we are also looking back through its history piece by piece, without ever being able to see it all at once in a single, unified moment. There is also the matter of attention. Our instruments and our research programs are guided by what we choose to look for. For a long time, astronomers focused on the brightest, most active parts of the Milky Way: star-forming regions, the galactic centre, the main spiral arms. These areas are visually striking and scientifically rich. They tell us about how stars are born, how black holes behave, and how gas flows through the galaxy. But by focusing on them, we naturally paid less attention to the faint, quiet outskirts. The halo, with its sparse population of old stars and dim streams, did not stand out in the same way. It required deeper surveys, more sensitive instruments, and a willingness to spend time and resources on regions that, at first glance, seemed relatively uneventful. This is not a flaw. It's a reflection of how exploration often works. We're drawn to the places where things are happening, the fireworks, not the empty sky around them. But as tools like James Webb allow us to see fainter and farther, our attention can shift. And when it does, our picture of the galaxy begins to change, not because the galaxy itself has changed, but because we are finally noticing parts of it that were always there. Another subtle limit comes from language itself. The words we use to describe the galaxy carry assumptions. We talk about the edge of the Milky Way as if it were a solid object with a boundary. We talk about the shape of the galaxy as if it were something you could hold in your hands and turn around. In reality, a galaxy is a distribution of matter and energy. Its density varies gradually. Its influence fades rather than stops. Its form depends on what component you're talking about. Stars, gas, dust, and dark matter all have different distributions. So when we say the Milky Way is a certain size, we're really saying that one particular component of it, usually the bright disk of stars, reaches out to a certain distance. Other components go much farther. This layered nature doesn't fit neatly into simple descriptions. It requires more nuanced language, and nuance can be harder to communicate, especially outside of technical contexts. There's also a cultural dimension to perspective. For most of human history, the Milky Way was not a scientific object. It was a feature of the night sky, woven into myths, stories, and spiritual beliefs. It was a path for souls, a river of light, a bridge between worlds. When science began to describe it as a galaxy, a system of stars bound by gravity, that didn't erase those older meanings, it added another layer to them. Even today, when we talk about our place in the galaxy, there's often a quiet emotional undertone. We are a small part of something vast. We're not at the centre. We're one star among hundreds of billions. This idea can feel humbling, comforting, or unsettling, depending on how you look at it. And those feelings can subtly shape how we engage with the science itself. There's a tendency, for example, to focus on the central regions of the galaxy, where the supermassive black hole resides, where star formation is intense, where things feel dramatic and important. The outskirts, by contrast, can seem like a quiet periphery, less interesting, less significant. But from another perspective, those outskirts are a record of the galaxy's history. They preserve the remains of ancient mergers and interactions. They hold some of the oldest stars, relics from the early days of the Milky Way's formation, so what seems peripheral from one point of view can be central from another. This shifting sense of what matters is another reflection of human perspective. We bring our own values, interests, and narratives to the way we study the universe. Even the technology we build reflects this. Telescopes are designed with specific goals in mind. Some are optimized for visible light, others for radio waves, others for infrared. Each one opens a window onto a different aspect of the galaxy. When a new window opens, like the one James Webb provides, it doesn't just add detail to an existing picture. It can change the picture itself by revealing features that were previously invisible. This is why the idea that the Milky Way might be larger than we thought is not just a technical update, it's a shift in perspective. It's a reminder that our mental image of the galaxy is shaped by what our tools allow us to see. There's a parallel here with everyday experience. Think about how a city feels different depending on how you explore it. If you only ever drive on the main roads, you get one impression. If you walk through side streets, parks, and neighbourhoods, you get another. Neither view is wrong, they're just partial. In the same way, our view of the Milky Way has been shaped by the main roads of astronomical observation, the bright stars, the active regions, the easily detectable structures. As we start to wander into the fainter, quieter areas, our sense of the whole changes. There is also the matter of scale within scale. The Milky Way itself is just one part of a larger structure, the local group of galaxies, which includes Andromeda, Triangulum, and dozens of smaller systems. That group is part of a larger filament of galaxies, which is part of a vast cosmic web stretching across the observable universe. So even as we struggle to fully grasp the scale of our own galaxy, that galaxy is just a node in a much larger pattern. This can lead to a kind of nested perspective, where every time you think you've reached the edge of something, you discover that it sits inside something even bigger. From the surface of Earth, the sky feels vast. From the perspective of the solar system, Earth's orbit is a small loop around a single star. From the perspective of the Milky Way, the solar system is a tiny point in a disk of hundreds of billions of stars. From the perspective of the universe, the Milky Way is one among trillions of galaxies. At each level, what felt large becomes small. This doesn't mean our original perspective was wrong. It just means it was limited by the scale at which we were operating. In science, recognizing those limits is part of the process. Every measurement, every model, every theory comes with a range of validity. It works well within certain conditions and less well outside them. When astronomers revise their estimates of the Milky Way's size, they are not admitting failure. They're doing what science is designed to do, adjusting the model to better fit the evidence. There's something quietly reassuring about that. It suggests that our understanding is not fixed, it can grow, and that growth often begins at the edges, in the places where our perspective is weakest. The faint stars at the outskirts of the galaxy, the subtle motions of distant satellite galaxies, the barely detectable glow of ancient stellar populations. These are the places where our assumptions are most likely to be challenged, because they are the places we have seen least clearly. James Webb's role in this story is not just that it sees farther, it sees differently. By working in infrared, it bypasses some of the barriers that shaped our earlier perspective. It reduces the influence of dust. It highlights cooler, fainter objects. It brings parts of the galaxy into view that were previously hidden in shadow. As those parts become visible, the balance of the picture shifts. The bright, familiar structures are still there, but they are now set within a larger, more extended context. And that, in turn, feeds back into how we think about our own position. We're not just in a spiral arm of a galaxy. We're in a layered, evolving system with a long history and a wide reach. We are part of a structure that extends far beyond what we can see with our eyes, or even with most of our instruments. This doesn't change the fact that your room is still the size it was when you started listening. The Earth is still turning. The night sky still looks much the same as it did before James Webb launched. But it adds a quiet, expanded background to those familiar experiences. When you look up at the Milky Way band, you can think of it not just as a stripe of light, but as the dense midsection of a much larger, more subtle presence that surrounds you on all sides. And if our perspective has limits, that doesn't make it useless. It makes it a starting point. Every new observation, every new instrument, every new model is a way of stepping a little farther from that starting point, gaining a slightly wider view. Long before any images began quietly appearing on computer screens in control rooms and research offices around the world, the idea of a new kind of space telescope existed mostly as a problem to be solved. Astronomers knew what they wanted. They wanted to see farther into dusty regions, deeper into the early universe, and more clearly into places where visible light simply could not go. What they did not yet know was how many years of design, testing, revision and patience it would take to turn that desire into something that could actually unfold itself in the vacuum of space and begin to observe the cosmos. The James Webb Space Telescope did not arrive as a sudden invention. It grew slowly, shaped by decades of experience with earlier observatories, and by the quiet realization that even our most successful instruments still left much of the universe hidden from view. To understand why Webb matters so much to the story of the Milky Way, it helps to step back for a moment and look at what came before it. The Hubble Space Telescope, launched in 1990, transformed astronomy. Its images of distant galaxies, nebulae and star-forming regions reshaped how the public and scientists alike thought about the universe. Hubble worked primarily in visible and ultraviolet light, with some ability to observe in the near-infrared. From its position above Earth's atmosphere, it avoided the blurring effects of air and moisture, producing crisp, detailed views of space that were impossible from the ground. But Hubble also had limits. Visible light is easily blocked by dust. In the Milky Way, especially along the dense plane of the disk, thick clouds of cosmic dust obscure large portions of the galaxy. Hubble could see the glowing edges of these clouds and the stars around them, but much of what lay inside and behind them remained hidden. Astronomers could detect the presence of stars forming inside these dusty regions through radio and infrared observations from other instruments, but those views often lacked the resolution and sensitivity needed to study them in detail. This gap between what could be inferred and what could be directly observed became one of the driving motivations behind Webb. The basic idea was simple in concept and complex in execution. If dust blocks visible light but allows infrared light to pass through, then a telescope optimized for infrared should be able to peer into regions of space that were otherwise obscured. It should be able to see cooler objects, like forming stars, distant galaxies whose light has been stretched into longer wavelengths by the expansion of the universe, and faint stellar populations in the outer reaches of galaxies. So the vision for Webb was not just a bigger Hubble, it was a different kind of eye. Building that eye required solving a series of engineering challenges that, at times, bordered on the absurd. One of the first decisions was size. To collect faint infrared light, Webb needed a large mirror. The larger the mirror, the more light it can gather, and the finer the detail it can resolve. Engineers settled on a primary mirror 6.5 meters across, more than 2.5 times the diameter of Hubble's. But there was a problem. No rocket available could carry a solid mirror that large into space. The solution was to make the mirror out of segments that could fold up for launch, and then unfold and align themselves in space. Webb's primary mirror is made of 18 hexagonal segments, each coated in a thin layer of gold to improve their ability to reflect infrared light. Once deployed, these segments had to line up with extraordinary precision. If even one of them was slightly out of place, the telescope's images would be blurred. To achieve this, Webb was equipped with a system of tiny actuators that could adjust the position of each segment by fractions of the width of a human hair. Then there was the issue of temperature. Infrared telescopes are extremely sensitive to heat. If the telescope itself is warm, it will emit infrared radiation that can overwhelm the faint signals coming from distant objects. To work properly, Webb needed to be kept incredibly cold. Hubble orbits Earth, which means it passes in and out of sunlight every 90 minutes. That constant heating and cooling would be disastrous for an infrared observatory. So Webb was sent far away, nearly 1 million miles from Earth, to a location known as the Second Lagrange Point, or L2. This is a spot in space where the gravitational pull of Earth and the Sun combine in a way that allows a spacecraft to orbit the Sun in sync with Earth. From this position, Webb can keep its sunshield facing the Sun, Earth, and Moon at all times, blocking their heat and light. On the other side of the shield, the telescope sits in permanent shadow, cooling down to temperatures just a few degrees above absolute zero. The sunshield itself is a marvel. It's about the size of a tennis court and made of 5 layers of a special material designed to reflect and radiate heat. Each layer is separated by a small gap, allowing heat to dissipate gradually as it moves outward. By the time any warmth reaches the telescope side, it has been reduced to almost nothing. The deployment of this sunshield, along with the unfolding of the mirror and the extension of various booms and antennas, was one of the most complex sequences ever attempted in space. Hundreds of individual steps had to occur in the correct order, many of them relying on motors, cables, and hinges that had never been tested in the vacuum of space before. For weeks after launch, engineers and scientists watched telemetry data as each component moved into place. There was no way to send a repair crew if something went wrong. Webb had to succeed on its own. When the last mirror segment locked into position and the final alignment adjustments were made, the telescope began its scientific mission. What emerged from that effort was an observatory with capabilities unlike any before it. Webb carries several instruments, each designed to analyze infrared light in different ways. Some take images, others break light into spectra, revealing the chemical composition, temperature, and motion of distant objects. Together, they allow astronomers to study everything from the atmospheres of exoplanets to the structure of galaxies at the edge of the observable universe. For the Milky Way, these instruments opened up a new way of seeing. Regions that had appeared as dark voids in visible light images began to show intricate structures in the infrared. Dense clouds of gas and dust, once seen only as silhouettes against glowing backgrounds, revealed networks of filaments, knots, and cavities carved by young stars. Star-forming regions that had been studied for decades suddenly looked different. Webb could detect the faint glow of protostars still wrapped in their natal cocoons. It could trace the distribution of molecules in the surrounding gas, offering clues about the chemistry that eventually leads to the formation of planets. But Webb's influence on our understanding of the Milky Way goes beyond these dramatic close-ups. One of its quieter strengths is sensitivity. Webb can detect extremely faint sources of infrared light, allowing it to see stars and stellar populations that were previously below the detection limits of other telescopes. This matters most in the outer regions of the galaxy. The halo of the Milky Way is populated by old, dim stars that emit much of their light in the infrared. These stars are spread thinly across vast distances, making them difficult to find and study. With Webb, astronomers can begin to pick out these faint points of light against the background of distant galaxies and cosmic infrared glow. By identifying and characterizing these halo stars, scientists can build a more complete picture of how far the Milky Way's stellar population extends. There is also the advantage of clarity. Infrared observations can cut through dust, reducing one of the biggest sources of uncertainty in distance measurements and star counts. This makes it easier to distinguish between stars that are truly part of the Milky Way and distant background galaxies that just happen to lie along the same line of sight. Webb does not work alone in this. Its data is often combined with information from other missions, especially Gaia, which measures the positions and motions of stars with incredible precision. Gaia tells astronomers where stars are and how they move. Webb helps reveal what those stars are like and where they sit in regions that Gaia struggles to see because of dust or faintness. Together, these two observatories create a kind of depth perception for the galaxy. Motion, position, brightness, and composition can all be considered at once, turning a flat star map into a three-dimensional dynamic model. This synergy has already begun to reveal structures in the Milky Way's outskirts that were difficult to confirm before. Streams of stars left behind by ancient mergers become easier to trace when their faint members can be detected more reliably. Subtle gradients in stellar populations across the halo can be studied, offering clues about when and where different parts of the galaxy formed. Even the distribution of dark matter can be inferred more accurately, because the motions of stars and satellite galaxies can be matched with a clearer picture of where visible matter actually resides. Another aspect of Webb's contribution is its ability to observe in multiple infrared wavelengths. Different materials and physical processes emit and absorb light at specific wavelengths. By looking at the same region in different parts of the infrared spectrum, astronomers can separate stars from gas, identify different molecules, and distinguish between warm and cool components. In the context of the Milky Way scale, this helps clarify what counts as part of the galaxy's structure. For example, some faint sources in the outer regions might be distant galaxies rather than nearby stars. Their infrared signatures can differ in subtle ways. Webb's spectral instruments can help make that distinction, reducing confusion and refining star counts in the halo. All of this adds up to a shift in how the Milky Way can be studied. Instead of relying primarily on visible light and radio observations, astronomers now have a powerful infrared window that fills in critical gaps. Regions that were once guesswork can be examined directly. faint populations that were once statistical estimates can be observed individually. The result is not just more detail, but a change in confidence. When you can see something rather than infer it, you can test your models more rigorously. It's worth noting that Webb was not built specifically to measure the size of the Milky Way. Its primary science goals include studying the early universe, the formation of galaxies, the birth of stars, and the atmospheres of exoplanets. The insights it provides about our own galaxy are, in a sense, a bonus. But because the Milky Way is a galaxy like any other, the same tools that allow Webb to study distant systems can also be turned inward. In some ways, our galaxy becomes a nearby laboratory, where processes that shape galaxies everywhere can be observed in detail. When Webb looks at the outskirts of the Milky Way, it is not just measuring how far the galaxy extends. It is also studying how galaxies grow, how they interact with their environment, and how they assemble their mass over time. This connection between the local and the cosmic is part of what makes Webb's observations so powerful. The same faint stars in our halo that help define the Milky Way's scale also tell a story about the history of the universe, because they formed in an era when galaxies were still coming together. The telescope's design reflects this dual purpose. Its large mirror and sensitive instruments are just as suited to detecting a tiny, cold exoplanet atmosphere as they are to picking out a faint star on the edge of our own galaxy. In both cases, the challenge is the same: find a small, subtle signal in a vast, complex background. From a more human perspective, there's something quietly remarkable about the way Webb operates. It does not take pictures in the way a camera does. It collects photons, tiny packets of energy that have travelled for years, centuries, or millennia before reaching its mirror. Those photons are then turned into electronic signals, processed into data, and eventually translated into images and graphs that we can interpret. By the time you see a Webb image on a screen, it has passed through layers of technology and human understanding. It is not a raw view of reality. It is a carefully constructed representation, shaped by the design of the instrument and the choices of the scientists who analyze the data. This doesn't make the images less real. It makes them part of a conversation between the universe and the people studying it. In the case of the Milky Way's scale, that conversation is still ongoing. Webb has begun to contribute new lines of evidence, but those findings are being tested, debated, and refined. Some studies suggest that the stellar halo is more extended and structured than previously thought. Others focus on specific regions, mapping out how far certain populations of stars can be traced. Still others use Webb's data to improve models of dust distribution, which in turn affects distance measurements across the galaxy. Each of these efforts adds another piece to the puzzle. What's notable is not that Webb has delivered a single definitive answer, but that it has expanded the range of questions that can be asked. Instead of simply asking, "How big is the Milky Way?" astronomers can now ask, "How does its size vary depending on which component we look at? How did its outer regions form? And how does its structure compare to that of similar galaxies in different environments?" These are more nuanced questions, and they reflect a deeper level of understanding. As Webb continues to operate, its role in this story will likely grow. More surveys of the galactic plane and halo are planned. More detailed studies of star streams and satellite galaxies will be carried out. Each new data set will be another opportunity to test and refine our picture of the galaxy. From the outside, this process can look slow. Discoveries are announced, then revised, then discussed again. But from the inside, it's a steady, careful expansion of knowledge, guided by evidence rather than expectation. In a way, Webb itself embodies the theme of scale. It is a human-made object, built on Earth, launched by a rocket, and operated by people sitting at desks and looking at screens. And yet, it reaches out across millions and billions of kilometers, gathering light from stars and galaxies that formed long before any of those people were born. When it turns its attention back toward our own galaxy, it becomes a tool for self-exploration on a cosmic level. It allows us to see our home from a new angle, not by stepping outside it, but by peering through the layers that once blocked our view. As those layers become more transparent, the Milky Way begins to look less like a neat, bounded object, and more like a sprawling, evolving system with a long, complex history. That shift in view does not happen all at once. It unfolds over time, observation by observation, analysis by analysis. Beneath the bright band of the Milky Way that stretches across the night sky, there lies another version of our galaxy that most human eyes will never see. It is not made of glowing stars and obvious shapes, but of shadowed regions, cold clouds, and fine grains of material drifting quietly between points of light. This hidden layer does not announce itself. It does not shine. It absorbs, scatters, and softens what passes through it, shaping our view of the galaxy in ways that are easy to overlook and hard to fully account for. Cosmic dust is one of the great organisers and one of the great obscurers of the Milky Way. The word dust might suggest something small and insignificant, but in space this material plays a central role in how galaxies look and how they evolve. It is made of tiny, solid particles, often smaller than a grain of smoke, composed of carbon, silicates, ice and trace metals. These particles form in the atmospheres of dying stars and in the debris of stellar explosions, then drift outward into the space between stars, where they become part of the raw material for future generations of suns and planets. Invisible light, dust, is a troublemaker. It blocks starlight. It dims distant objects. It creates dark lanes and patches that cut through otherwise bright regions of the galaxy. Some of the most striking images of the Milky Way show these inky shapes snaking across glowing starfields, like silhouettes of something solid against a luminous background. From a scientific point of view, those silhouettes are both a clue and a barrier. They tell us where dense clouds of material are located, but they also prevent us from seeing what lies behind them. For decades, large portions of the galaxy, especially toward the central regions, were effectively hidden from optical telescopes. Astronomers knew that something was there, but they could only guess at the details. To understand how profound this effect is, it helps to think about how light behaves when it encounters dust. Visible light has relatively short wavelengths. When it strikes a dust particle, it can be absorbed or scattered in different directions. Over long distances, this process can remove a large fraction of the light from a beam travelling toward Earth. The farther that light travels through dusty regions, the dimmer and redder it becomes, because shorter, bluer wavelengths are scattered more efficiently than longer, redder ones. This effect, called interstellar reddening, is one of the main reasons distant stars often appear redder than they truly are. It also means that some stars become so dim in visible light that they effectively disappear from view, even though they are still there. Infrared light behaves differently. Its longer wavelengths allow it to slip past many of the dust particles that block visible light. It is not completely immune to absorption, but it is far less affected. This makes infrared astronomy a powerful tool for exploring the hidden parts of the galaxy. When James Webb was designed, this property of infrared light was one of its main advantages. It was built to look through the dusty veil that has shaped our view of the Milky Way for generations. Before Webb, astronomers relied on a patchwork of infrared observations from ground-based telescopes and earlier space missions. These provided important insights, but they were limited in resolution and sensitivity. They could show large-scale structures, but not always the fine detail needed to understand how those structures fit together. Webb changed that balance. With its large mirror and highly sensitive instruments, it can collect faint infrared light from distant and obscured regions, resolving individual stars and structures that were previously blurred or invisible. This capability opens up a different way of seeing the galaxy, one that is less dominated by the brightest, least obscured regions and more inclusive of the quieter, hidden ones. One of the most dramatic examples of this comes from star-forming regions. In visible light, many of these areas look like dark, irregular clouds. They appear as holes in the star field, places where something seems to be missing. In reality, those clouds are packed with gas and dust, and inside them, new stars are being born. As a star begins to form, it gathers material from its surroundings, growing hotter and denser. At first, it is completely wrapped in a thick cocoon of dust and gas that blocks almost all visible light. Only when it becomes hot and energetic enough to blow away or heat up that surrounding material does it begin to shine in the optical range. Infrared light can escape much earlier. With Webb, astronomers can see into these cocoons and observe stars at very early stages of their development. They can trace the shapes of the clouds, the filaments of material feeding the growing stars, and the cavities carved out by stellar winds and radiation. These observations are not just visually striking, they help scientists understand how efficiently stars form in different parts of the galaxy, how mass is distributed, and how energy flows through the interstellar medium. And this, in turn, relates back to the scale of the Milky Way. A galaxy's size is not just a matter of how far its stars extend, it is also about how its material is organised and how it cycles through different phases. Gas and dust are constantly being transformed into stars, and stars, when they die, return material back to the interstellar medium. This cycle happens across the entire galaxy, from the crowded central regions to the faint outskirts. By seeing through the dust, Webb allows astronomers to study this process in places that were previously difficult to access, giving a more complete picture of how the Milky Way sustains itself across its full extent. Another important aspect of dust is that it is not evenly distributed. In the Milky Way's disk, dust tends to concentrate along the spiral arms, where gas is denser and star formation is more active. This creates long, dark lanes that trace the structure of the arms themselves. In visible light images of other spiral galaxies, these dust lanes are often seen as thin, dark lines winding around the bright cores. Because we are inside the Milky Way, we see these lanes from the side rather than from above. They show up as broad, irregular bands and patches that can stretch across large portions of the sky. This uneven distribution of dust creates a kind of observational bias. Regions of the galaxy that happen to lie behind thick dust clouds are underrepresented in visible light surveys. Regions with clearer lines of sight are overrepresented. If you try to count stars or map structures using only visible light, you will naturally get a picture that is shaped by where the dust happens to be. Infrared observations help correct this bias. By comparing how a region looks in visible and infrared light, astronomers can estimate how much dust lies along that line of sight. This allows them to adjust the apparent brightness of stars and get a better sense of their true luminosity and distance. Over large areas of the galaxy, these corrections can make a significant difference in star counts and distance estimates. That in turn affects how far the disk and halo appear to extend. In some cases, regions that once seemed sparsely populated turn out to be rich in stars that were simply hidden behind dust. This has particular importance near the galactic centre. The core of the Milky Way is one of the most crowded and dust-obscured regions in the sky. In visible light, it is largely invisible. Thick clouds of dust block our view, leaving only a few bright stars and glowing patches to hint at what lies beyond. Infrared telescopes have gradually peeled back this curtain over the years, revealing a dense cluster of stars and the presence of a supermassive black hole at the centre. Webb adds another layer of clarity to this picture. It can resolve stars in the central region with greater detail, study the distribution of gas and dust around the black hole, and trace how material moves and interacts in this extreme environment. While this may seem far removed from the question of the galaxy's overall size, it is part of the same story. The centre of the Milky Way is a key anchor point for models of the galaxy's structure. Knowing its mass, motion, and distribution of stars helps define the orbits of everything else. Better data about the centre leads to better models of the disk and halo, and ultimately, better estimates of how far the galaxy's influence extends. Dust also plays a role in how we distinguish between stars in the Milky Way and distant background galaxies. When looking toward the outskirts of the galaxy, especially at high galactic latitudes, astronomers often encounter faint, small sources of light. Some of these are dim stars in the halo. Others are entire galaxies far beyond the Milky Way. In visible light, these can look very similar. Both appear as tiny, blurry points. Infrared observations can help tell them apart. Distant galaxies often have different infrared signatures than nearby stars. Their light has been stretched by the expansion of the universe, shifting it into longer wavelengths. They may also show the combined glow of billions of stars and warm dust within the galaxy itself. By analysing the infrared spectrum of a faint source, astronomers can determine whether it is likely a halo star or a distant galaxy. This reduces confusion and makes star counts in the outer regions of the Milky Way more reliable, and those star counts are a crucial ingredient in determining how far the galaxy extends. Another layer of darkness that Webb helps address is not caused by dust at all, but by temperature. Many objects in space are simply too cool to emit much visible light. Low-mass stars, brown dwarfs, and certain types of stellar remnants shine primarily in the infrared. These objects can be numerous, especially in older populations like the galactic halo. Because they are faint and cool, they are easy to miss in optical surveys, but they still contribute to the galaxy's mass and structure. By detecting these cooler objects, Webb helps fill in another part of the picture, revealing a population of stars that were always there but often overlooked. This matters when astronomers try to estimate the total number of stars in the Milky Way and the distribution of mass across the galaxy. If a significant fraction of stars are faint and cool, then visible light surveys alone will underestimate their presence, especially in distant or obscured regions. As more of these objects are detected, the apparent size and richness of the galaxy's stellar population can increase. Darkness, in another sense, also refers to the vast stretches of space between stars. The Milky Way is not a solid mass of light. It is mostly empty. Even in the dense regions of the disk, the average distance between stars is several light years. In the halo, those distances grow much larger. This emptiness can make the outskirts of the galaxy difficult to define. When stars become very sparse, it becomes harder to tell where the galaxy ends and intergalactic space begins. Infrared sensitivity helps here as well, by allowing astronomers to detect stars that are both faint and isolated. A single star in the far halo might emit so little light that it blends into the background noise in visible light images. In the infrared, it can stand out just enough to be identified and studied. Each such detection extends the known reach of the galaxy by a small amount. Over many observations, these small extensions can add up to a significant revision of the galaxy's scale. There is also the role of dust in shaping how we think about structure. Because dust tends to trace spiral arms and star-forming regions, our mental image of the Milky Way shape has been influenced by where the dust appears. Dark lanes in visible images often mark the locations of arms. Bright regions highlight areas of active star formation. When infrared observations reveal stars behind those lanes, it can change how those structures are interpreted. What once looked like a gap between arms might turn out to be a region filled with stars that were simply hidden from view. This can lead to adjustments in how the number and shape of spiral arms are modelled, which in turn affects the perceived size and geometry of the disk. Another interesting aspect of dust is its temperature. Dust grains absorb energy from nearby stars and re-emit it in the infrared. By measuring this emission, astronomers can estimate the temperature and density of dust clouds. Webb's instruments can map these properties across different regions of the galaxy, revealing variations that hint at different environments and histories. In the outer parts of the galaxy where star formation is less active, dust tends to be cooler and more diffuse. Detecting this faint emission can be challenging, but it provides information about how far the galaxy's interstellar medium extends. If dust and gas are found far from the bright disk, it suggests that the galaxy's material envelope reaches farther into space than previously thought. This, again, feeds back into the question of scale. There is also the interplay between dust and dark matter. While dust itself does not interact directly with dark matter, both are influenced by the galaxy's gravitational potential. The distribution of dust and gas can trace the underlying shape of the dark matter halo in subtle ways, especially in how material flows and settles over time. By mapping dust and gas in the outskirts of the galaxy, astronomers can test models of the halo's shape and extent. Webb's ability to detect faint dust emission and obscured stars provides new data for these tests, helping refine our understanding of the invisible structure that holds the galaxy together. From a more human standpoint, there is something quietly poetic about the idea that much of the Milky Way's true form has been hidden behind a veil of dust, waiting for a different kind of light to reveal it. For centuries, people looked up at the night sky and saw a glowing band, a river of stars. That view was shaped by the dust that both blocked and highlighted different parts of the galaxy. Now, with infrared eyes, we are beginning to see beyond that surface, into the deeper layers that were always there but out of reach. This does not replace the old view, it adds to it. The visible Milky Way is still real. It is still the way the galaxy presents itself to human eyes on a clear night. The infrared Milky Way is another aspect of the same structure, one that reveals different features and different stories. Together, they form a more complete picture. As astronomers continue to combine data from Webb with observations from other telescopes across the electromagnetic spectrum, they are building a kind of multi-layered map of the galaxy. Each wavelength adds its own layer of information. Radio waves trace cold gas. Infrared light reveals dust and cool stars. Visible light shows hot young stars and glowing nebulae. Ultraviolet light highlights energetic processes and massive stars. When these layers are stacked together, the Milky Way becomes not just a shape in space, but a complex system of interacting components, each with its own distribution and scale. And in that layered system, the idea of a single, simple boundary becomes harder and harder to maintain. The galaxy does not end at the last bright star or the last visible cloud. It fades gradually, through populations of older stars, through thin streams of material, through a dark matter halo that extends far beyond anything that emits light. By seeing through dust and darkness, Webb helps illuminate parts of that gradual fade, making the transition from galaxy to intergalactic space less abrupt and more nuanced. This is one of the subtle ways in which a telescope can change not just what we know, but how we think about what we know. Instead of asking for a single number to describe the Milky Way's size, astronomers increasingly talk about different scales for different components: the stellar disk, the stellar halo, the gas halo, the dark matter halo. Each of these has its own extent, its own structure, and its own uncertainties. Infrared observations feed into all of these by revealing stars, dust, and gas in regions that were previously difficult to study. As that information accumulates, the picture of the Milky Way becomes less like a neat diagram and more like a landscape with gradual transitions and overlapping regions. That landscape is still being mapped. Every new deep survey, every new targeted observation adds a few more points of light to the map, a few more threads to the network of streams and clouds and clusters that make up the galaxy's outskirts. Across parts of the sky that many people recognize without ever thinking too deeply about them, there are stretches of space that look calm, almost empty, as if the galaxy has taken a quiet breath there. These are the regions between the bright knots of constellations, the areas where the Milky Way's glowing band thins out and the stars seem to step back from center stage. For a long time, those familiar-looking patches were treated as relatively unremarkable, background scenery rather than places where something new might be found. What James Webb has been helping to reveal is that unremarkable can be a very misleading word. Hidden among those familiar star fields are populations of stars that do not announce themselves easily. They are faint, they are cool, they often sit behind thin layers of dust or blend into the soft glow of the galaxy's background light. To the human eye, and even to many older instruments, they fade into the scenery. But when you start to look at these regions with sensitive infrared vision, a different picture begins to emerge. some of the stars that Webb detects are simply small. Low-mass stars, especially red dwarfs, make up the majority of the Milky Way's stellar population. They are dim compared to stars like the Sun, and many of them emit much of their light in the infrared rather than in visible wavelengths. From a distance, these stars are almost invisible to optical telescopes. A red dwarf in the outer parts of the galaxy might be so faint in visible light that it barely registers as more than a point of noise in an image. In the infrared, however, it can stand out just enough to be identified as a real, physical object. Multiply that by millions, and you begin to see how large portions of the galaxy's true population could have been undercounted. This matters because when astronomers try to estimate the size and structure of the Milky Way, they rely heavily on star counts. Where stars are plentiful, the galaxy feels present. Where they become sparse, the galaxy seems to fade. If a significant number of stars are simply too faint to be seen with older methods, then the apparent edge of the galaxy may have been drawn closer than it should have been. Webb's sensitivity helps push that edge outward, not by discovering new stars in the sense of creating them, but by making existing ones visible to us for the first time. Another group of hidden stars comes from age rather than size. The Milky Way is not made up of a single generation of stars. It is a layered structure built over billions of years. Some stars are young, hot, and bright, shining with a bluish light and surrounded by glowing clouds of gas. Others are ancient, small, and cool, having formed in the early days of the galaxy's history. These older stars often populate the halo and the thick disk, regions that are more diffuse and less visually striking than the main spiral arms. Because they are cool and dim, they are much easier to detect in the infrared than in visible light. When Webb observes familiar-looking areas of the sky and begins to pick out these older stars, it adds depth to what once seemed like a flat background. A patch of sky that might have looked like a sparse scattering of bright stars can turn out to be a layered region, with multiple populations at different distances and belonging to different parts of the galaxy's structure. This depth changes how astronomers think about the Milky Way's shape. Instead of seeing the galaxy as a disk with a thin halo, they begin to see it as a more complex extended system, where different stellar populations overlap and interweave. Some of these hidden stars also carry signatures of the galaxy's past. In the outer regions of the Milky Way, astronomers have found stars that do not quite match the chemical composition of stars formed in the main disk. They have different ratios of elements like iron, carbon, and alpha elements, which suggest they were formed in environments with different histories of star formation and supernova explosions. These stars are thought to be the remnants of smaller galaxies that were absorbed by the Milky Way long ago. As those galaxies were pulled apart by gravity, their stars were scattered into long, faint streams that now wrap around the halo. In visible light, many of these streams are difficult to trace, especially where they pass behind dust or blend into crowded starfields. Infrared observations can help separate the members of these streams from the surrounding stars by highlighting subtle differences in brightness and colour that correlate with age and composition. By mapping these hidden structures, astronomers are effectively uncovering the galaxy's family tree, seeing not just what the Milky Way is, but how it became what it is. There are also stars that are hidden not because they are faint or old, but because they are deeply embedded in dust. Star formation is a messy process. When a region of gas begins to collapse under its own gravity, it pulls in dust along with it. The result is a dense, opaque cloud that can block visible light almost completely. Inside these clouds, new stars are forming, growing, and heating up, but their light cannot escape in the optical range. To a visible light telescope, these regions look like dark voids. In the infrared, they become rich, detailed landscapes. Webb's images of these areas show clusters of young stars at different stages of development, some still wrapped in thick envelopes of material, others beginning to clear out their surroundings with radiation and stellar winds. These young stars are often found in regions that are already familiar, places that have been studied for decades in visible light. What changes is not the location, but the level of detail. A well-known nebula might suddenly reveal dozens or hundreds of faint protostars that were previously invisible. A dark lane across the Milky Way might turn out to be a complex network of filaments, feeding multiple star-forming regions. While these discoveries are more about the internal life of the galaxy than its overall size, they still feed into the bigger picture. The distribution of star formation affects how the galaxy's mass is arranged over time. Where stars form, how many form, and how long they live all influence the density and structure of the disk and halo. Another subtle source of hidden stars comes from motion. Some stars in the Milky Way move at speeds that set them apart from their surroundings. These could be stars that were flung out of dense clusters by gravitational interactions, or remnants of past mergers that are still travelling along distinct paths through the halo. Because these stars may pass through regions that are otherwise sparsely populated, they can be easy to miss. Their light may be faint, and their presence may not significantly change the overall brightness of a patch of sky. By combining Webb's infrared sensitivity with motion data from missions like Gaia, astronomers can identify these stars more reliably. A faint point of light that might otherwise be ignored can be recognized as a star with a unique trajectory, marking it as part of a larger structure or event in the galaxy's history. These moving stars act like breadcrumbs, tracing out the paths of past interactions and helping define the extent of the galaxy's gravitational reach. There is also the matter of stellar remnants. Not all stars shine brightly forever. When stars like the Sun reach the end of their lives, they shed their outer layers and leave behind a dense core called a white dwarf. These objects are small, hot at first, and then gradually cool over billions of years. Older white dwarfs can be extremely faint, especially in visible light, but they still emit in the infrared, particularly when they are part of a population of ancient stars in the halo. Detecting these remnants helps astronomers estimate how many stars have lived and died in different parts of the galaxy. This, in turn, provides clues about the galaxy's formation history and the distribution of mass over time. If large numbers of white dwarfs are found far from the bright disk, it suggests that star formation was more widespread in the past, or that stars have been redistributed by mergers and gravitational interactions. Another category of hidden objects includes brown dwarfs, sometimes called failed stars. These are objects that formed like stars but never became massive enough to ignite sustained hydrogen fusion in their cores. They glow faintly, primarily in the infrared, and can be difficult to detect even with sensitive instruments. Brown dwarfs are thought to be numerous, especially in the disk and possibly in the halo. If they make up a significant fraction of the galaxy's population, they contribute to its mass and structure without adding much visible light. By finding and studying these objects, Webb helps fill in another piece of the galaxy's inventory, revealing matter that was largely invisible to earlier surveys. All of this contributes to a gradual shift in how astronomers think about familiar regions of the sky. A constellation that has been known for thousands of years might still look the same to the naked eye, but in the infrared it can become a layered scene with stars at multiple distances, embedded clusters, faint streams, and cool objects that add depth and complexity. This layered view has implications for how distances are measured. If a region contains multiple overlapping populations of stars, some in the disk, some in the halo, and some in the background, it becomes more challenging to assign a single distance to that patch of sky. Each population needs to be separated and analysed on its own terms. Webb's ability to detect faint stars and characterise their properties helps make this separation more accurate. By determining which stars belong to which population, astronomers can build more precise three-dimensional maps of the galaxy. These maps, in turn, affect estimates of the galaxy's size. If stars belonging to the Milky Way are found at greater distances in a given direction than previously thought, the boundary of the galaxy in that direction moves outward. This does not necessarily mean the galaxy is perfectly symmetrical. Different regions may extend farther or fall off more quickly, depending on the distribution of stars, gas, and dark matter. But each new detection of a distant hidden star adds another data point to the outline of the galaxy. There is also a more subtle effect related to perception. When a region of the sky is known to contain only a few bright stars, it tends to be thought of as empty. When new stars are found there, the mental map of the galaxy changes. This can influence how astronomers design future surveys and where they focus their attention. Regions once considered low priority can become areas of interest, leading to more detailed studies and further discoveries. In this way, the act of finding hidden stars can create a feedback loop. Discovery leads to attention leads to more data, and more data leads to a more complete picture. From a broader perspective, this process highlights a recurring theme in the study of the universe. Much of what exists is not immediately obvious. It requires specific conditions, specific tools, and specific questions to be revealed. The Milky Way, as seen with the naked eye, is already a remarkable sight. But it is only a surface layer of a much deeper structure. Infrared observations peel back some of that surface, showing that even in places we thought we knew well, there are still layers of complexity waiting to be explored. There is also an emotional dimension to this idea. The stars that are hidden today may have been shining for billions of years, long before humans existed, long before the Earth took its current form. They have been part of the galaxy's story all along, even if we're only now becoming aware of them. In that sense, the process of discovery is not about changing the universe. It is about changing ourselves, expanding what we notice and what we consider part of our environment. When you look up at the night sky and see a familiar pattern of stars, it can be quietly striking to think that behind that pattern, layered in depth and distance, there are countless other stars that you cannot see, each with its own history and place in the galaxy. Those stars still contribute to the gravity that holds the Milky Way together. They still move along their orbits. They still influence the shape and evolution of the galaxy. Their hidden presence is a reminder that the galaxy's true scale is not just a matter of measuring how far its brightest parts reach. It is also about recognizing how much of it exists in a faint, subtle form that only becomes visible when we learn how to look differently. As Webb continues to survey familiar regions with its infrared instruments, it is likely to keep finding these quiet additions to the galaxy's map. Each one is small on its own, a single star or cluster, but together they build up a more extended and nuanced outline of the Milky Way. Out beyond the places where star charts usually start to thin and familiar labels begin to disappear, the Milky Way takes on a character that feels less like a neatly drawn object and more like a suggestion, a presence that fades rather than stops. This is the region where recent observations, especially those informed by James Webb's quiet reach into faint and dusty corners, have begun to reshape how astronomers talk about the galaxy's overall form. For a long time, the Milky Way was described with a kind of comfortable confidence. A disk of stars, a central bulge, a surrounding halo, and beyond that, the emptiness of intergalactic space. It was a simple framework, easy to teach, easy to visualize, and broadly accurate in its essentials. But as more data has accumulated, that framework has started to feel less like a clean diagram and more like a rough sketch, useful, but missing important detail. The first hint that the galaxy might be wider than expected came from star counts in the outer disk. Astronomers began to notice that in some directions, stars belonging to the Milky Way could be detected farther out than models predicted. These were not bright, obvious stars. They were faint, often old, and easy to miss. But their presence suggested that the disk did not taper off as quickly as once thought. In some regions, the stellar density declined more gradually, extending the apparent edge of the disk by thousands of light years. This did not mean that the disk suddenly doubled in size. It meant that the transition from inside the galaxy to outside the galaxy was more gradual and uneven than a single number could capture. Webb's infrared sensitivity added another layer to this picture. By detecting faint stars that emit most of their light at longer wavelengths, it helped fill in parts of the outer disk and inner halo that were underrepresented in visible light surveys. This made the galaxy feel not just wider in a flat radial sense, but thicker and more layered. The idea of depth is important here. The Milky Way is often pictured as a flat spiral, but in reality it has a vertical structure. The thin disk where most of the gas, dust and young stars reside is embedded in a thicker disk of older stars. Surrounding both is the halo, a roughly spherical distribution of ancient stars and globular clusters. Each of these components has its own scale. The thin disk is only a few hundred light-years thick in its densest regions. The thick disk extends a few thousand light-years above and below the plane. The halo reaches tens or even hundreds of thousands of light-years into space. When Webb and other instruments begin to detect faint stars far above or below the galactic plane, they are adding to the sense that the Milky Way's vertical reach is more substantial and more structured than earlier maps suggested. Some of these stars appear to belong to the thick disk, others to the inner halo. Their motions, ages and chemical compositions help astronomers sort them into different populations, each with its own origin story. This layering creates a galaxy that is not just wider in the sense of having a larger diameter, but deeper in the sense of having a more extended and complex three-dimensional form. Then there is the halo itself, which has become one of the most intriguing and, in some ways, the strangest parts of the Milky Way structure. For a long time, the halo was thought of as a relatively smooth, spherical cloud of old stars and globular clusters, a kind of faint envelope around the bright disk. But as surveys have become more detailed, that smoothness has started to break down. Instead of a uniform distribution, the halo appears to be threaded with streams, clumps, and subtle variations in density. These features are the remains of smaller galaxies and star clusters that were pulled apart by the Milky Way's gravity over billions of years. Each stream is a record of an ancient interaction, a trail of stars that once belonged to another system and now follow elongated orbits around the galaxy. Webb's ability to detect faint stars helps make these streams easier to trace, especially in regions where dust or background light made them difficult to see before. By mapping them, astronomers can begin to piece together a more detailed history of how the Milky Way grew, and that history is one of gradual assembly rather than simple formation. The galaxy we see today is not a single structure that formed all at once. It is the result of countless mergers, accretions, and gravitational encounters. Each of these events added stars, gas, and dark matter to the system, often in uneven ways. This means that the galaxy's shape is not perfectly symmetrical. In some directions, the halo extends farther. In others, it is more compact. Some regions are rich in streams and substructures, others are relatively smooth. So when astronomers talk about the Milky Way's true scale, they're not just talking about a single radius or diameter. They're talking about a complex, lopsided, evolving form that does not lend itself to a simple boundary. The word stranger fits here because the more detail is revealed, the less the galaxy resembles the tidy mental image many of us grew up with. Consider the idea of a spiral arm. In diagrams, spiral arms are often drawn as smooth, continuous curves wrapping gracefully around the galactic center. In reality, they are not solid structures. They are patterns in the distribution of gas, dust, and young stars, more like traffic jams in a rotating disk than permanent physical arms. Stars move in and out of these patterns over time. Gas piles up, forms stars, and then drifts away. The arms themselves can shift, split, or fade as the galaxy evolves. When Webb looks at these regions in infrared, it can reveal stars behind the dust lanes that define the arms in visible light. This can make the arms appear less like sharp features and more like broad, fuzzy regions with complex internal structure. That fuzziness adds to the sense that the galaxy's shape is not a clean, well-defined object, but a dynamic pattern in motion. There is also the matter of the galaxy's outermost stars. Some of the stars detected in the far halo have orbits that take them incredibly far from the center, sometimes hundreds of thousands of light-years out. These stars may spend most of their time in regions where the galaxy's gravitational pull is weak, influenced not just by the Milky Way, but by the combined gravity of the local group of galaxies. In these outer zones, the distinction between belonging to the Milky Way and belonging to the intergalactic environment becomes blurred. This blurring makes the idea of a hard edge feel less and less appropriate. Instead, the galaxy seems to fade into a broader gravitational landscape, where its influence overlaps with that of Andromeda and other nearby systems. The two largest galaxies in the local group are already interacting through their dark matter halos, even though their visible disks are still more than 2 million light-years apart. This interaction is subtle and slow, but it is real. It means that on the larger scales, the Milky Way is not an isolated island, but part of a connected system of galaxies that are gradually moving toward a future merger. From this perspective, the true scale of the Milky Way includes not just its stars and gas, but its role in a larger cosmic neighborhood. Webb's observations of distant galaxies provide a useful comparison here. By studying other spiral galaxies in different environments, astronomers can see how size and structure vary. Some galaxies have very extended halos, others are more compact. Some show clear signs of recent mergers, others appear relatively undisturbed. When these observations are combined with detailed studies of the Milky Way, patterns begin to emerge. Our galaxy appears to be fairly typical in some respects, but it also shows signs of a particularly active history of interactions. The richness of its halo substructures, for example, suggests that it has absorbed a significant number of smaller galaxies over its lifetime. This helps explain why the halo might be more extended and more complex than earlier models assumed. Another layer of strangeness comes from the relationship between visible matter and dark matter. The stars and gas we can see make up only a small fraction of the galaxy's total mass. The majority is in the form of dark matter, which does not emit or absorb light. The shape of the dark matter halo influences the orbits of stars and satellite galaxies, and thus indirectly shapes the visible structure of the Milky Way. Models of the dark matter distribution suggest that the halo may be much larger than the region populated by stars. In some estimates, it could extend out to several 100,000 light-years, or even close to 1 million light-years, blending into the dark matter halos of neighbouring galaxies. If this is the case, then the true scale of the Milky Way, in terms of its gravitational influence, is far larger than the scale defined by its stars alone. Webb does not detect dark matter directly, but by providing better data on the motions and distribution of stars in the halo, it helps constrain these models. The more accurately astronomers can trace stellar orbits at large distances, the better they can infer the shape and extent of the underlying dark matter. This interplay between the visible and the invisible adds a kind of quiet mystery to the galaxy's form. Much of what defines its size is something we cannot see, only feel through its effects. There is also a temporal dimension to this widening and deepening view. The Milky Way we see today is a snapshot in a long process of growth and change. Its size is not fixed. It has been increasing over time as it absorbs material from its surroundings. In the distant past, the galaxy was smaller, less massive, and more chaotic. Over billions of years it pulled in gas, formed stars, and merged with smaller systems, gradually building up the structure we recognize now. The halo, in particular, is a kind of fossil record of this process. The streams and clumps of stars found there are the remains of those ancient building blocks. By mapping these features, astronomers can reconstruct a timeline of the galaxy's growth, seeing not just how big it is now, but how it became that big. This historical perspective adds to the sense of strangeness, because it turns the galaxy into something more like a story than a static object. It has chapters, episodes, and turning points written in the motions and compositions of its stars. When Webb reveals a faint stream of stars in the halo, it is not just extending the map. It is uncovering a past event, a moment when another galaxy passed too close and was slowly torn apart. These events can have lasting effects on the Milky Way structure, creating ripples in the disk, altering the distribution of stars and contributing to the overall mass and scale. Even the disk itself shows signs of these interactions. Surveys have revealed that the Milky Way's disk is warped and rippled, with waves of stars moving up and down relative to the galactic plane. These waves are thought to be the result of past encounters with satellite galaxies or dark matter clumps. This means that the galaxy's flat spiral shape is actually a bit wavy and uneven, adding another layer of complexity to its three-dimensional form. From a distance, if one could somehow see the Milky Way from the outside, it might look less like a perfect pinwheel and more like a slightly distorted layered structure with faint extensions and asymmetries that hint at its long and active history. All of this contributes to the feeling that the galaxy is not just bigger than we thought, but also more intricate. The more closely it is studied, the more it reveals that its size is not just a matter of distance, but of structure, history, and interaction. There is also a human element in how this strangeness is perceived. We tend to like clear categories, inside and outside, near and far, part of the galaxy and not part of the galaxy. The Milky Way challenges these categories. Its boundaries are fuzzy, its components overlap, its influence extends beyond its visible form. As our instruments improve, we are forced to confront this ambiguity more directly. James Webb's contribution is not that it provides a single, definitive measurement of the galaxy's size. It is that it helps reveal the galaxy as a more extended, layered and interconnected system than a simple number can capture. This can feel unsettling, but it can also feel expansive. Instead of living in a neatly bounded cosmic home, we appear to be part of something that blends gradually into a larger environment, a system of galaxies that are themselves part of an even larger cosmic web. From that perspective, the Milky Way is not just a place. It is a region in a continuous structure of matter and energy that stretches across the universe. As this view takes shape, it naturally raises questions about what all of this means for our own position within the galaxy. If the Milky Way is wider and deeper than we thought, if its influence and structure extend far beyond the bright band we see in the sky, then where exactly do we fit within this expanded picture? Instead of picturing the Milky Way as a fixed symbol on a page, it can be more useful to think of it as something closer to a living framework, a structure that holds together through motion, gravity and time rather than through rigid lines and clear edges. This shift in how the galaxy is imagined has been quietly gaining momentum as new observations, including those influenced by James Webb's ability to reveal faint and obscured regions, begin to challenge the simplicity of older models. For much of the last century, the shape of the Milky Way was described in terms that were easy to draw. A central bulge, a flat disk, a set of spiral arms, a surrounding halo. Each part had its place, and together they formed a neat, almost architectural design. That model was never wrong exactly, it was just incomplete. What is becoming clearer is that each of those components is more flexible, more textured, and more intertwined than a simple diagram can convey. The galaxy's shape is not a static outline. It is the result of countless motions happening all at once, layered over billions of years. One place where this becomes especially apparent is in the disk itself. The disk is often described as flat, but careful measurements have shown that it is warped and rippled. In some regions, the outer parts of the disk bend upward. In others, they dip downward. This warp is not a small detail. It spans tens of thousands of light years and affects how stars and gas are distributed across the galaxy. There are a few likely causes for this distortion. One is the gravitational influence of nearby satellite galaxies, particularly the large and small Magellanic Clouds. As these smaller galaxies orbit the Milky Way, they tug on its outer disk, creating waves that propagate inward over time. Another possible contributor is the uneven distribution of dark matter in the halo. If the dark matter is not perfectly symmetrical, it can create subtle forces that pull different parts of the disk in different directions. The result is a galaxy that is not a perfectly level plane, but something more like a gently flexing sheet, responding to forces from both within and beyond. This alone changes the way the galaxy's shape needs to be understood. Instead of a rigid disk, it becomes a dynamic surface, one that can bend, ripple, and slowly shift. Then there are the spiral arms. In popular imagery, spiral arms are often shown as solid, continuous structures, like the arms of a pinwheel. In reality, they are better described as patterns of higher density moving through the disk. Stars, gas, and dust orbit the center of the galaxy at different speeds depending on their distance from the center. The spiral pattern moves at its own pace, and as material passes through it, gas clouds compress, triggering bursts of star formation. This creates the bright, young stars that make the arms stand out. But those stars do not stay in the arms forever. Over time, they drift away, becoming part of the general disk population. This means that the arms themselves are not fixed features. They can change shape, split, fade, and reform over long timescales. Infrared observations add another layer to this picture by revealing stars behind the dust lanes that often define the arms in visible light. When those hidden stars are taken into account, the boundaries of the arms become less sharp. What once looked like a clear division between arm and interarm region can turn out to be a more gradual transition. This makes the galaxy's shape feel less like a set of well-defined bands and more like a continuous flowing distribution of matter. The central region of the Milky Way also resists simple description. At its heart lies a dense bulge of stars, along with a supermassive black hole that has a mass of about 4 million suns. For a long time, the bulge was thought to be roughly spherical, a kind of swollen center around which the disk was wrapped. More detailed studies have shown that this region is actually elongated, forming a bar-like structure that stretches across the center of the galaxy. This bar plays a significant role in the movement of gas, channeling material inward and influencing where stars form. The shape of this bar is not perfectly straight or uniform. It has its own internal structure, with different populations of stars moving in different ways. Some stars follow elongated orbits aligned with the bar. Others move in more circular paths around the center. This complexity means that even the very core of the galaxy cannot be reduced to a simple geometric form. And then there is the halo, which in many ways is the most challenging part of the galaxy's shape to define. The halo is often described as spherical, but that description is more a convenience than a precise statement. Observations suggest that it may be somewhat flattened or elongated, and that its density varies in different directions. More importantly, the halo is not smooth. It is threaded with streams of stars, remnants of smaller galaxies that were absorbed by the Milky Way over billions of years. These streams trace out long looping paths that wrap around the galaxy, sometimes passing close to the disk, sometimes extending far into the outer regions. Each stream has its own orientation, its own shape, and its own history. Together they form a kind of three-dimensional web around the galaxy. This web-like structure makes it difficult to talk about the halo as a single, unified shape. Instead, it becomes a collection of overlapping features, each one adding to the overall form but also complicating it. When James Webb helps detect faint stars in these streams, it adds detail to this web, making the halo's structure more apparent and more intricate. Another factor that reshapes how the galaxy's form is understood is the distribution of gas. Gas in the Milky Way is not confined to the thin disk. There is also a halo of hot, diffuse gas extending far above and below the plane of the galaxy. This gas is difficult to detect because it is faint and spread out, but it plays an important role in the galaxy's life cycle. It acts as a reservoir of material that can eventually cool and fall back into the disk, fueling future star formation. It also interacts with outflows from supernovae and stellar winds, creating a complex circulation of matter between the disk and the halo. The presence of this gas halo adds another layer to the galaxy's shape. one that is not visible in starlight but still influences the galaxy's mass, motion, and evolution. If you include this component, the Milky Way becomes not just a collection of stars and dark matter, but a multi-phase system of stars, cold gas, warm gas, hot gas, dust, and invisible matter, all arranged in overlapping interacting structures. This multi-layered nature makes the idea of a single, definitive shape feel increasingly inadequate. There is also the matter of orientation. When we draw the Milky Way, we usually show it from above, looking down on the disk. This perspective is useful, but it is not one we can ever actually have. From our position inside the galaxy, we see it from the side, looking along the plane of the disk. This internal perspective emphasizes some features and hides others. For example, the spiral arms are hard to trace from within because we are looking through them rather than at them from above. The halo is even harder to visualize, because it surrounds us on all sides, blending into the background of distant galaxies. This means that our mental image of the galaxy's shape is always a reconstruction, a model built from indirect evidence. As new data fills in more of the three-dimensional structure, that reconstruction becomes more complex. One of the ways this complexity shows up is in the realization that different parts of the galaxy can be misaligned with each other. The disk, the bar, the halo, and the dark matter distribution may not all share the same center or orientation. Small offsets and tilts between these components can have significant effects on how stars and gas move. These misalignments can be caused by past mergers, by the ongoing influence of satellite galaxies, or by the initial conditions under which the galaxy formed. Accounting for them makes the galaxy's shape feel less like a single, coherent object, and more like a system of interacting parts, each with its own history and dynamics. There is also the influence of the broader cosmic environment. The Milky Way is part of the Local Group, a collection of galaxies bound together by gravity. The largest members of this group, the Milky Way and Andromeda, are moving toward each other and will eventually merge in a few billion years. Even now, their dark matter halos likely overlap, creating a shared gravitational region that extends far beyond the visible stars of either galaxy. This overlap means that the outermost parts of the Milky Way's halo are not entirely its own. They exist in a space where the influence of Andromeda and other nearby galaxies is also present. This further blurs the boundary between our galaxy and the space around our galaxy. From this perspective, the shape of the Milky Way cannot be fully described without considering its relationship to its neighbours. There is a kind of hierarchy of shapes at work. The shape of the disk is influenced by the halo. The shape of the halo is influenced by the local group. The shape of the local group is influenced by the larger cosmic web of galaxies and dark matter filaments. Each level nests within the next, creating a structure that is both local and universal at the same time. Another way to think about this is in terms of motion. Every star in the Milky Way is moving. The Sun orbits the centre of the galaxy at about 220 kilometers per second. Other stars move faster or slower depending on their orbits. Gas clouds swirl, collapse, and expand. Satellite galaxies trace long looping paths. If you could take a long exposure photograph of the galaxy over millions of years, its shape would blur and smear into something quite different from a static image. The spiral pattern would wind and unwind. Streams in the halo would stretch and thin. The warp in the disk would shift. This dynamic nature means that the shape of the galaxy is always, in some sense, a temporary state. When astronomers redefine the Milky Way's form, they are not finding a final answer. They are capturing a snapshot of a process. James Webb's contributions fit into this dynamic picture by providing new information about parts of the galaxy that were previously undersampled. Faint stars in the halo, obscured regions in the disk, and cool objects that emit primarily in the infrared all add to the three-dimensional map. As these data points accumulate, the galaxy's shape becomes less like a simple figure and more like a volume filled with structures at different densities and orientations. This shift in thinking also affects how the galaxy is represented in educational and public contexts. Diagrams that show a neat spiral with a few arms and a round halo are still useful. They convey the basic idea, but they now come with an implicit asterisk, a recognition that the real structure is more complex. There is a balance to be struck between clarity and accuracy. Too much detail can overwhelm, too little can mislead. The evolving picture of the Milky Way's shape is a case study in how scientific understanding often moves. Simple models give way to more nuanced ones as data improves, and those nuanced models, in turn, open up new questions. For example, if the halo is highly structured and extended, what does that say about the galaxy's merger history? How many smaller systems did it absorb? When did those events occur? If the disk is warped and rippled, how long do those features last? Are they constantly being refreshed by ongoing interactions, or are they fading remnants of past encounters? If the dark matter halo is asymmetric, what does that imply about the distribution of dark matter on larger scales? Each of these questions ties the shape of the Milky Way to broader themes in cosmology and galaxy formation. They connect our local environment to processes that operate across the universe. From a more reflective standpoint, there is something quietly humbling about this shift. The galaxy that once seemed like a familiar backdrop, a fixed home with a known outline, becomes something more like a landscape that is still being explored. Its form is not fully charted. Its boundaries are not clearly marked. Its history is still being pieced together. In that sense, redefining the shape of our galactic home is not just a technical exercise. It is a reminder that even the largest structures we can meaningfully talk about are, in some ways, still mysterious. We live inside a system that is bigger, more layered, and more dynamic than our first impressions suggest. As new observations continue to refine that picture, the Milky Way becomes less like a static map and more like a story in progress. From the quiet orbit of a small, ordinary star on the outskirts of a vast and layered system, the idea that the Milky Way might be larger and more extended than we once believed carries a different kind of weight. It is one thing to talk about a galaxy in abstract terms as a structure measured in light years and billions of stars. It is another to realize that this expanded picture is the environment through which our own solar system has been traveling, slowly and steadily, for its entire existence. The sun is not anchored in place, it is moving. Along with the planets, asteroids, comets, and distant clouds of icy debris that make up the solar system, it follows a long looping path around the centre of the Milky Way. This journey is sometimes called a galactic year, and it takes about 230 million Earth years to complete one full orbit. That means that since complex life began to appear on Earth, the Sun has not even made a single full trip around the galaxy. In the time it takes for continents to drift, species to rise and fall, and civilizations to emerge and disappear, the solar system is still tracing out the same broad arc through the Milky Way's disk. When the scale of the galaxy is revised upward, when its halo is found to stretch farther and its structure to be more layered, it subtly changes how this journey is understood. The solar system is not just moving through a flat, star-filled disk. It is moving through a three-dimensional environment that includes overlapping populations of stars, clouds of gas and dust, and an extended halo of ancient objects and dark matter. To picture this, it helps to step away from the familiar idea of a circular orbit in a flat plane and think instead of a path through a volume. The Sun's orbit is tilted slightly relative to the main plane of the galaxy. Over time it moves up and down, passing above and below the densest part of the disk. These vertical oscillations take tens of millions of years, carrying the solar system through regions of different stellar density and different concentrations of gas and dust. In a galaxy that is more extended and more structured than previously thought, these vertical and radial movements take on added significance. When the Milky Way was imagined as a relatively simple disk with a modest halo, the solar system's environment seemed fairly uniform on large scales. It moved through a general field of stars, occasionally passing near spiral arms where star formation was more active, but otherwise remaining in a broadly similar setting. As the picture of the galaxy grows wider and deeper, that sense of uniformity begins to fade. The solar system's path now looks more like a journey through a layered landscape, where different regions have different properties and histories. Some of these regions are denser, with higher concentrations of stars and gas. Others are more sparse, part of the thick disk or the inner halo. Each of these environments can, in subtle ways, influence what happens within the solar system. One of the most discussed connections between the galaxy and the solar system involves comets. Far beyond the orbit of Pluto, the solar system is surrounded by a vast spherical cloud of icy objects known as the Oort cloud. This region extends tens of thousands of astronomical units from the Sun, far enough that the Sun's gravitational grip is relatively weak. In this distant zone, the gravity of passing stars, clouds of gas, and even the overall gravitational field of the galaxy can disturb the orbits of these icy bodies, sending some of them inward toward the inner solar system. When the Milky Way is understood as having a more extended and massive halo, the gravitational environment around the solar system becomes part of a larger picture. The overall gravitational field of the galaxy, shaped largely by dark matter, influences how tightly the Oort cloud is held together. Changes in that field, such as those caused by the solar system passing through different regions of the galaxy, can affect how often comets are nudged toward the inner planets. This does not mean that the galaxy is constantly showering Earth with comets in a dramatic way. The effects are subtle and play out over millions of years. But they are part of the background conditions that shape the long-term history of the solar system. There is also the matter of nearby stars. As the Sun moves along its orbit, it passes through different stellar neighbourhoods. Most of the time, the nearest stars are several light years away, and their gravitational influence on the solar system is negligible. But occasionally a star passes relatively close on a cosmic scale. These encounters can also disturb the outer regions of the solar system, particularly the Oort cloud, increasing the likelihood of comets being sent inward. In a galaxy with a more extended and complex structure, the distribution of stars in the regions the solar system passes through may be more varied than previously thought. The solar system's journey is not just a smooth path through a uniform field, but a passage through regions shaped by past mergers, streams of stars, and subtle variations in density. This adds another layer of nuance to how astronomers think about the long-term dynamical environment of the solar system. Another connection between the galaxy's scale and the solar system involves radiation. The Milky Way is not a quiet place in energetic terms. Supernovae, the explosive deaths of massive stars, occur regularly somewhere in the galaxy. These events release enormous amounts of energy and high-energy particles into space. Most of the time, these explosions happen far enough away that their effects on the solar system are minimal, but over geological timescales there may have been supernovae close enough to Earth to influence the planet's environment, potentially affecting its atmosphere or climate. If the Milky Way structure includes extended regions of star formation that were previously underappreciated, it could influence how astronomers model the distribution and frequency of such energetic events. The solar system's position in the galaxy, about 26,000 light-years from the centre, places it in a relatively calm region compared to the crowded active core. But as the understanding of the galaxy's scale and structure becomes more detailed, the context of that calm can be refined. For example, the solar system's distance from the galactic centre and its position relative to spiral arms can be considered alongside the distribution of halo stars, gas clouds, and dark matter structures. This broader context helps astronomers evaluate how typical or atypical our galactic environment might be. There is also the question of chemical history. The elements that make up the Earth, the Sun, and everything living on this planet were forged in earlier generations of stars. When those stars ended their lives, they returned those elements to the interstellar medium, where they became part of new stars and planetary systems. The distribution of these elements across the galaxy is not uniform. Regions that have experienced more star formation and more supernovae tend to be richer in heavier elements. Regions that are more isolated or have had fewer such events tend to be more chemically primitive. As the Milky Way structure is mapped in greater detail, including its extended halo and streams of stars from past mergers, it becomes possible to trace how different parts of the galaxy have contributed to the overall chemical makeup of the interstellar medium. The solar system formed from a cloud of gas and dust that had been enriched by previous generations of stars. Understanding where that cloud came from and what kind of galactic environment it was embedded in is part of understanding how the conditions for planets and life arose. If the galaxy's halo contains remnants of smaller galaxies with different chemical histories, and if material from those systems has mixed into the disk over time, then the solar system's ingredients may reflect a broader galactic heritage than once assumed. Another way to think about the new scale of the galaxy is in terms of motion through time. The Milky Way is not static. It is moving through the local group of galaxies, and its own internal structure is evolving. Over billions of years, the positions of spiral arms shift, satellite galaxies merge, and streams of stars are stretched and dispersed. The solar system's path is embedded in this larger flow. If the galaxy's halo is more extended and structured, then the gravitational landscape through which the solar system moves is also more complex. The Sun's orbit is influenced not just by the mass of the disk and bulge, but by the distribution of dark matter and the presence of massive structures in the halo. These influences are small on human timescales, but over millions and billions of years, they shape the overall trajectory of the solar system. This long-term perspective can make the solar system feel less like an isolated bubble and more like a traveller in a vast interconnected system. There is also a shift in how home can be understood. For much of modern astronomy, the solar system's address was given in simple terms: a planet orbiting a star located in a spiral arm of the Milky Way, one of many galaxies in the universe. As the picture of the Milky Way grows more detailed and more expansive, that address becomes more layered. The solar system is part of the thin disk. The thin disk is embedded in a thick disk. Both are surrounded by a halo of ancient stars and dark matter. That halo overlaps with the halos of neighbouring galaxies. Those galaxies are part of a group. That group is part of a larger filament of galaxies. Each layer adds context to the one below it. This does not change the practical reality of life on Earth. The sun still rises and sets. The seasons still change. The night sky still looks much the same as it did before these new observations, but it changes the background story. When you look up at the stars, you're not just looking at a flat pattern of points. You're looking into a deep layered structure that extends far beyond what the eye can see, and that includes regions and populations of stars that were, until recently, largely unknown. There is also a subtle effect on how astronomers think about the search for life elsewhere. The habitability of a planetary system can be influenced by its galactic environment. Regions with very high rates of star formation and supernova activity might be more hazardous for life, due to increased radiation and gravitational disturbances. Regions that are too isolated might lack the heavier elements needed to form rocky planets in the first place. By refining the map of the Milky Way structure and scale, scientists can better understand where different kinds of environments exist within the galaxy. The solar system's position, in a relatively quiet part of the disk with a moderate abundance of heavy elements, appears to be a favourable one for the development of complex life. As the galaxy's extended halo and streams are studied in more detail, it becomes possible to compare our local environment to those of stars that formed in very different parts of the galaxy, or even in different galaxies that were later absorbed. This comparative approach can help identify what aspects of the solar system's history are typical and what might be more unusual. There is also a connection to the future. The Milky Way and Andromeda are on a slow collision course. In about 4 billion years, they will begin to merge, eventually forming a single, larger galaxy. In that distant future, the structure and scale of the Milky Way will change dramatically. The disk will be disrupted, the halo will be reshaped, streams of stars will be mixed and scattered. The solar system will still be there, orbiting within this evolving structure, although its path and environment will be altered. Understanding the Milky Way's current scale and structure helps set the stage for understanding how this future transformation might unfold. It also places the solar system's present situation in a much longer narrative, one that stretches from the early assembly of the galaxy to its eventual merger with a neighbour. On a more immediate human level, there is something quietly grounding about connecting the small and the large in this way. The objects in the solar system, the Earth, the Moon, the planets, the distant comets, all feel tangible. They can be seen, touched indirectly, or visited by spacecraft. The galaxy, by contrast, feels abstract and remote. By understanding how the two are linked, how the solar system moves within the Milky Way's extended structure and responds to its gravitational and energetic environment, that sense of separation softens. The solar system becomes part of a continuous system rather than a small isolated island. This perspective can also influence how astronomers interpret the past of the solar system. There are clues in the geological record on Earth, in the distribution of craters on the Moon, and in the composition of meteorites that hint at changes in the rate of impacts or the influx of material over time. Some of these changes may be connected to the solar system's movement through different regions of the galaxy, such as passing through denser clouds of gas or near spiral arms. As the Milky Way structure is mapped in greater detail, it becomes possible to model these journeys more accurately, linking events in the solar system's history to specific galactic environments. This does not mean that every major event on Earth can be traced back to a galactic cause. Many things are driven by local processes, but it does mean that the broader galactic context is part of the story. Another aspect to consider is how the new sense of scale affects our emotional relationship to the cosmos. There is a long tradition in science and philosophy of reflecting on humanity's place in the universe. Discoveries that expand the known size of the cosmos often come with a sense of humility. When the Earth was found to orbit the Sun, and the Sun was found to be one star among many, and the Milky Way was found to be one galaxy among billions, each step reduced our apparent centrality. The realization that even our own galaxy is more extended and more complex than we thought continues that trend. It suggests that our home is larger, more layered, and more interconnected than we previously imagined. This does not make human experiences smaller in a meaningful sense. It simply places them within a broader framework. From the perspective of the Milky Way's extended halo, the solar system is a tiny, moving point. From the perspective of a human life, the solar system is a stable, enduring environment. Both perspectives are true at the same time. As astronomers continue to refine their understanding of the galaxy's scale, the relationship between the solar system and the Milky Way will likely become even more detailed. New surveys may reveal additional structures in the halo, new streams of stars, or subtle variations in the dark matter distribution that influence the Sun's long-term path. Each of these discoveries will add another layer to the story of how the solar system fits into the galaxy. In the end, what the new scale of the Milky Way means for our solar system is not a dramatic change in daily reality. The planets will not shift in their orbits because a telescope has revealed more distant stars. But it does change the narrative context. The solar system becomes part of a larger, more extended and more intricate system than the one that existed in our mental maps before. It becomes a traveller in a vast layered structure that stretches far beyond the bright band of the Milky Way we see in the night sky. Maps are usually made with the comforting assumption that the place being mapped will stay still long enough for the ink to dry. Roads don't slide across the page. Rivers may bend over centuries, but not while you're drawing them. Mountains stay put, at least on human timescales. A map, once finished, can sit on a wall and remain useful for years, even decades, without changing very much. A galactic map does not have that luxury. The Milky Way is not a fixed landscape. It is a moving system, a vast collection of stars, gas, dust and dark matter, all orbiting, drifting and evolving at different speeds and on different paths. Trying to draw a map of something like that is less like sketching a city, and more like trying to chart the shape of a slow, shifting cloud. At the heart of this challenge is the relationship between time and distance. In everyday life, distance is something you can cross. You walk across a room, you drive across a town. Time passes, but the place itself doesn't fundamentally change while you're moving through it. In astronomy, distance is also time. Light takes time to travel. The farther away something is, the farther back in time you're seeing it. This simple fact turns every observation of the Milky Way into a kind of time travel. When you look at a star that is 1,000 light years away, you're seeing it as it was 1,000 years ago. When you observe the centre of the galaxy, 26,000 light years away, you're seeing a version of that region that existed when human civilization was just beginning to develop agriculture. When astronomers try to assemble a map of the galaxy, they are not working with a single snapshot. They are piecing together views from many different moments in the past. That alone would be complicated enough, but the galaxy itself is changing during those times. Stars move along their orbits, gas clouds collapse and disperse, spiral patterns shift, satellite galaxies pass by and leave behind streams of stars. The structure being mapped is in motion even as its light is on its way to us. So a galactic map is not a picture of the Milky Way at one moment. It is a collage of moments, stitched together into something that approximates the present. This creates a subtle but important tension. On the one hand, the galaxy evolves slowly. Over the span of a human lifetime, or even over the few decades that modern astronomy has been active, the large-scale structure of the Milky Way does not change dramatically. The spiral pattern remains, the disk and halo remain. The overall distribution of stars looks much the same. On the other hand, when you're working with timescales of tens of thousands or hundreds of thousands of years, small motions can add up. A star in the disk can move a significant fraction of its orbit in that time. A stream in the halo can stretch and thin. Gas clouds can form new stars and be reshaped by their radiation. So when light from different parts of the galaxy reaches Earth, it is carrying information from different stages of this ongoing process. Astronomers account for this by treating the galaxy as if it were, for the most part, in a steady state. This is a reasonable approximation for many purposes. The Milky Way is not undergoing a dramatic, sudden transformation at the moment. It is changing gradually. But the approximation has limits. As observations become more precise and reach farther into the halo and the outskirts of the galaxy, those limits start to matter more. Subtle differences in timing and motion can affect how features are interpreted. Consider something as seemingly simple as a star stream in the halo. A stream is made up of stars that once belonged to a smaller galaxy, or star cluster, that was pulled apart by the Milky Way's gravity. Those stars now follow similar orbits, forming a long, thin structure that wraps around the galaxy. When we observe a stream, we are seeing different parts of it at different times. The stars closer to us are being seen more recently. The stars farther away are being seen further back in time. Because the stream is moving and stretching, the shape we observe is not exactly the shape it has at any single moment. It is a time-smeared version of the structure. This does not make the observation useless. It just means that interpreting it requires careful modelling of how the stream moves and evolves over time. The same is true for the disk. When astronomers map the spiral arms, they are tracing patterns in the distribution of gas and young stars. Those patterns are dynamic. They shift and change as material moves through the galaxy. The arms we see in one part of the galaxy are not necessarily in exactly the same configuration as the arms in another part, because we are seeing them at slightly different times. This can lead to apparent irregularities or mismatches in the map that are not necessarily real features of the galaxy, but artifacts of the time delay in the observations. Then there is the problem of scale. The Milky Way is so large that no single method can map it completely. Astronomers use a combination of techniques, each of which works best in a particular range of distances. Parallax measurements provide very precise distances for nearby stars, out to a few thousand light-years. Beyond that, standard candles and other methods take over, with larger uncertainties. For the outer halo and distant satellite galaxies, distances may be estimated based on models of motion and gravity rather than direct measurement. Each of these layers of the map has its own resolution and its own error bars. When they are combined into a single picture, those differences can create distortions. It is a bit like stitching together photographs taken with different cameras and lenses. Some parts of the image will be sharp and detailed, others will be grainy or slightly blurred. The transitions between them can be tricky to handle. Astronomers work hard to calibrate these different data sets so that they align as well as possible. But there is always some level of uncertainty in how the pieces fit together. Another challenge comes from the fact that the Milky Way is not evenly populated. In some regions, stars are packed closely together. In others, they are sparse. The density can change dramatically over relatively small distances, especially in the halo and the outer disk. This unevenness means that some parts of the galaxy are easier to map than others. In a dense star field, there are many data points to work with. In a sparse region, a single star can carry a lot of weight in defining the structure. If that star is misclassified or its distance is measured incorrectly, it can shift the apparent boundary of the galaxy in that direction. This is one reason why the discovery of faint distant stars with instruments like James Webb can have an outsized impact on models of the galaxy's scale. Each new reliable detection in the outskirts adds a point to the map where previously there might have been nothing. Over time, these points can change the perceived shape and extent of the Milky Way. There is also the issue of perspective. Because we are inside the galaxy, we see it from a very specific vantage point. Our view is heavily influenced by our position in the disk, about 26,000 light-years from the centre. This internal perspective means that some features are always going to be easier to see than others. For example, the far side of the galaxy is harder to study because its light has to pass through the dense, dusty regions near the centre to reach us. Even in the infrared, that path is not completely clear. As a result, the near side of the disk is often better mapped than the far side. This can create asymmetries in galactic maps that reflect observational bias, rather than true differences in structure. Astronomers try to correct for this by using models and by comparing observations in different directions, but the bias can never be completely eliminated. Then there is the problem of distinguishing between what belongs to the Milky Way and what does not. When you look out toward the edge of the galaxy, you are also looking beyond it. Distant galaxies, quasars, and other extragalactic objects appear in the same field of view as faint halo stars. Separating these populations is not always straightforward, especially when dealing with very faint sources. Infrared observations help, as do measurements of motion. Stars in the Milky Way will show proper motion across the sky over time, while distant galaxies will not. But these measurements require long-term data and high precision. Until that information is available, some sources may be misidentified, affecting the map. The problem of galactic maps is not just technical, it is also conceptual. When people think of a map, they often imagine something with clear boundaries and labels. This city ends here. That river starts there. This country has a border at this line. The Milky Way does not have borders in that sense. Its density of stars and gas fades gradually. Its dark matter halo extends far beyond its visible components. Its gravitational influence overlaps with that of neighbouring galaxies. So any attempt to draw a line around the galaxy is, to some extent, an arbitrary choice. Astronomers may define the edge of the galaxy based on where the stellar density drops below a certain level, or where the gravitational influence of the Milky Way becomes weaker than that of Andromeda, or where the dark matter halo is thought to taper off. Each of these definitions produces a different map. This means that when new observations suggest the galaxy is larger than previously thought, what is often changing is not the physical galaxy itself, but the definition of which part of it is being emphasized. If you start including more of the halo, or if you refine your estimate of the dark matter distribution, the map grows. This flexibility can be confusing, especially outside of scientific contexts, where people may be looking for a single, definitive answer to the question, how big is the Milky Way? In reality, there are several answers, each corresponding to a different component of the galaxy. The disk has one size, the stellar halo has another, the gas halo has another, the dark matter halo has yet another. A galactic map that tries to include all of these components has to be multi-layered, more like a set of transparent sheets than a single flat image. Another complication comes from the tools used to make these maps. Modern galactic cartography relies heavily on large surveys that collect data on millions or billions of stars. Missions like Gaia provide incredibly detailed information about the positions and motions of stars, but they are optimized for certain types of observations. Gaia, for example, works primarily in visible light and is most sensitive to stars in the disk and nearby halo. It struggles in regions of very high dust density and in detecting very faint cool stars. James Webb, on the other hand, excels in the infrared and can see into dusty regions and detect faint objects, but it does not survey the entire sky. Its field of view is relatively small, and its observations are targeted rather than comprehensive. So each instrument provides a different piece of the map, and those pieces have to be combined. This combination process is complex. It involves matching stars across different catalogues, reconciling different distance scales, and accounting for different selection effects. Selection effects are biases introduced by the way a survey is conducted. For example, a survey that only detects stars brighter than a certain limit will naturally miss fainter stars, which can skew the apparent distribution. Correcting for these effects requires careful statistical modelling and assumptions about the underlying population. As the galaxy's map extends farther into the halo and the outskirts, these corrections become more important, because the stars being studied are often right at the limits of detectability. Another layer of complexity comes from the fact that not all parts of the galaxy are equally well studied. Some regions have been the focus of multiple surveys and detailed follow-up observations. Others have only been observed in passing. This uneven coverage can create gaps in the map, areas where the structure is inferred rather than directly observed. Webb's targeted observations can help fill in some of these gaps, especially in dusty or faint regions. But because its time is limited and its field of view is small, it cannot by itself create a complete, uniform map of the galaxy. Instead, it adds depth and detail to specific areas, which then have to be integrated into the broader picture. This process of integration is ongoing. Astronomers constantly update their models of the Milky Way as new data comes in. Distances are revised. Structures are reinterpreted. Features that were once thought to be separate may turn out to be connected, or vice versa. This means that a galactic map is never truly finished. It is more like a living document, a representation that evolves as our tools and understanding improve. There is something quietly fitting about this. The Milky Way itself is not finished. It is still forming stars. It is still interacting with its neighbours. It is still growing and changing. A map that captures it perfectly, once and for all, would almost feel out of place. From a more reflective point of view, the problem of galactic maps highlights a broader theme in science. We often talk about knowing something, but that knowledge is always provisional. It is based on the best available evidence and the best available models, and it is always open to revision. When new observations extend the known size of the Milky Way, they are not overturning everything that came before. They are refining it, adding layers and nuance. This can be seen as a kind of dialogue between the universe and the people studying it. The universe presents itself in the form of light, motion, and structure. Scientists respond by building instruments, creating models, and drawing maps. Those maps, in turn, guide the next round of questions and observations. Time and distance play a role on both sides of this dialogue. The light that reaches us carries information from the past. The maps we draw influence the future of research. In the context of the Milky Way's scale, this dialogue is particularly vivid. Each new detection of a distant star, each refined measurement of a halo stream, each improved model of the dark matter distribution adds a small piece to the map. Over time, these pieces accumulate, and the outline of the galaxy grows more extended, more complex and more detailed. But the process never quite reaches a point where it can stop and declare itself complete. There will always be fainter stars, more distant structures, and subtler motions to discover. In that sense, a galactic map is less like a finished product and more like a path. It is a way of organising what we currently know, while leaving room for what we have yet to learn. As James Webb and other observatories continue to add new information to this evolving picture, the Milky Way's map will continue to change. Not in sudden, dramatic shifts, but in small, steady adjustments that gradually reshape how the galaxy is understood. Across the vast range of galaxies scattered through the observable universe, the Milky Way has always occupied an interesting middle ground. It has never been considered a giant among giants, like the enormous elliptical galaxies that dominate the centres of galaxy clusters. At the same time, it has never been seen as a small or fragile system, like the faint dwarf galaxies that orbit larger hosts or drift quietly through intergalactic space. It has long been described as a fairly typical spiral galaxy, substantial, well-structured, and comfortably average in many respects. As new observations refine the Milky Way's true scale and reveal a more extended, layered, and complex structure, that sense of typical begins to shift in subtle ways. The first step in comparing our galaxy to others is deciding what features to compare. Galaxies come in a wide range of shapes and sizes. Some are spirals, with disks and arms like the Milky Way. Others are ellipticals, smooth and rounded, often filled with older stars and little gas. Still others are irregular, lacking a clear structure and shaped by interactions and internal turbulence. Even within the category of spiral galaxies, there is enormous variety. Some have tightly wound arms and bright central bulges. Others have loose, sweeping arms and relatively small cores. Some are rich in gas and actively forming stars. Others are more sedate, having used up much of their star-forming material. For a long time, the Milky Way was thought to sit comfortably among the larger spiral galaxies, but not at the extreme end of the scale. Its bright disk, about 100,000 light-years across, placed it in a similar category to galaxies like Andromeda and Triangulum, though Andromeda was generally considered slightly larger and more massive. As the picture of the Milky Way's halo and dark matter distribution becomes more detailed, that comparison becomes more nuanced. One of the most important measures of a galaxy's size is not just how far its stars extend, but how much mass it contains. Most of a galaxy's mass is not in its stars or gas, but in its dark matter, halo. This halo shapes the orbits of stars and satellite galaxies and determines how strongly the galaxy interacts with its neighbours. Estimates of the Milky Way's total mass have varied over the years, partly because the halo is difficult to study. The farther out you go, the fewer stars and satellites there are to use as tracers of the gravitational field. As new data, including observations of faint halo stars and the motions of distant satellite galaxies, improve these estimates, the Milky Way appears to be more massive than some earlier models suggested. This has implications for how it compares to other galaxies. If the Milky Way's dark matter halo is larger and more massive, then its gravitational reach is greater. This can influence how it interacts with nearby systems, how it captures or disrupts satellite galaxies, and how it fits into the larger structure of the local group. In terms of mass, the Milky Way and Andromeda are now thought to be more comparable than previously believed, though there is still uncertainty about which one is truly the heavier of the two. This near parity between the two largest members of the local group paints a picture of a future merger between roughly equal partners, rather than a small galaxy being absorbed by a much larger one. That future event, sometimes called Milkomeda or Milkdromeda, will reshape both galaxies, blending their stars, gas, and dark matter into a single, larger system. Looking outward, beyond the local group, astronomers study thousands of other galaxies to see where the Milky Way fits into the broader population. Large surveys of the sky have revealed that spiral galaxies of similar mass and brightness to the Milky Way are fairly common. They often reside in small groups rather than in the dense cores of galaxy clusters. This environment matters. Galaxies and clusters are subjected to strong gravitational interactions and hot, dense gas that can strip away their own gas and shut down star formation. They often evolve into elliptical or lenticular shapes. Galaxies in smaller groups, like the Milky Way, tend to retain their gas for longer and continue forming stars over extended periods. This makes the Milky Way's continued star formation, moderate spiral structure, and extended halo consistent with what astronomers see in other group environments. What has become more interesting is the level of structure and substructure in the Milky Way's halo. As observations reveal more streams and remnants of past mergers, the Milky Way begins to look like a particularly active collector of smaller galaxies. This is not unique. Many large galaxies show evidence of similar processes. In deep images of nearby galaxies, astronomers can see faint tidal streams and shells of stars around their outskirts, signs of past interactions. These features are often extremely faint and require long exposures to detect. The Milky Way, being so close, allows these features to be studied in much greater detail. When Webb and other instruments help trace the halo structure, they are providing a level of insight into galaxy growth that is hard to achieve for more distant systems. This has a feedback effect on how other galaxies are interpreted. If the Milky Way's halo is more extended and more structured than previously thought, it suggests that other spiral galaxies of similar mass may also have complex, far-reaching halos that are simply difficult to detect at great distances. In that sense, the Milky Way becomes a kind of reference point, a nearby example that can inform models of galaxy formation and evolution more broadly. Another area of comparison involves the distribution of stars within the disk. The Milky Way's disk appears to be fairly typical in terms of its thickness and star formation rate compared to other spiral galaxies of similar mass. It is not a starburst galaxy, where stars are forming at an exceptionally high rate. It is also not a quiescent galaxy, where star formation has largely ceased. It sits in a middle range, forming a few new stars per year, a pace that seems to be common among similar systems. What has changed with improved mapping is the sense of how far the disk and thick disk extend. If the Milky Way's stellar populations reach farther out than once thought, it may place the galaxy toward the larger end of the scale for disk galaxies. This does not necessarily make it exceptional, but it does suggest that its structure is more expansive than the simple, tidy picture often presented. There is also the matter of chemical composition. By comparing the chemical makeup of stars in the Milky Way to those in other galaxies, astronomers can learn about the history of star formation and enrichment. The Milky Way shows a range of metallicities, with stars near the centre and in the thin disk generally richer in heavy elements, and stars in the halo and thick disk often more primitive. This pattern is seen in many other spiral galaxies as well. What makes the Milky Way especially valuable is the level of detail that can be achieved, because we can study individual stars in our own galaxy, rather than just the combined light of billions of stars. We can trace chemical gradients and variations with much higher resolution. This detailed view helps calibrate methods used to study more distant galaxies, where such fine-grained analysis is not possible. In terms of overall appearance, if an observer could somehow view the Milky Way from outside, it would likely resemble many of the spiral galaxies seen in deep field images. It would have a bright barred centre, a set of spiral arms, and a faint extended halo. What would be harder to see, without long sensitive exposures, are the subtle features in the halo, the streams, shells, and faint stellar populations that hint at the galaxy's complex history. These features are now known to be common in large galaxies, but the Milky Way's proximity allows them to be studied in much greater detail than in most other systems. Another point of comparison is the galaxy's role within its local environment. The Milky Way and Andromeda dominate the local group, along with a few dozen smaller galaxies. This is a relatively small and loose association compared to massive clusters like the Virgo cluster, which contains thousands of galaxies bound together by gravity. In clusters, galaxies experience frequent interactions, high-speed encounters, and the influence of hot diffuse gas that fills the space between them. In the local group, interactions are less violent and more gradual. This environment allows galaxies like the Milky Way to maintain their disks and continue forming stars over long periods. The extended halo and complex structure of the Milky Way can be seen, in part, as a product of this environment. It has had time to grow through mergers with smaller galaxies without being subjected to the disruptive forces present in dense clusters. When astronomers compare the Milky Way to spiral galaxies in different environments, they often find that group galaxies tend to have richer halos and more pronounced signs of past mergers than isolated galaxies. This fits with the idea that small groups provide a steady supply of satellite galaxies that can be absorbed over time. Looking beyond the local universe, surveys of distant galaxies show that galaxy formation and evolution have changed over cosmic time. In the early universe, galaxies were generally smaller, more irregular, and more actively forming stars. Mergers were more common, and structures were less settled. As the universe aged, galaxies grew, disks formed, and star formation rates declined. The Milky Way's extended halo and layered structure can be seen as the outcome of this long process. It is a mature galaxy, one that has had billions of years to assemble its mass, form its disk, and accumulate a complex halo of stars and dark matter. In this context, the Milky Way serves as an example of what a large spiral galaxy can look like in the later stages of cosmic history. Comparisons with distant galaxies allow astronomers to place our own galaxy on a kind of evolutionary timeline. By looking at galaxies at different distances, and therefore at different points in the past, scientists can infer how systems like the Milky Way might have looked when they were younger. This, in turn, helps interpret the structures seen in the Milky Way's halo as relics of earlier phases of growth. Another interesting comparison involves the presence of satellite galaxies. The Milky Way has dozens of known dwarf companions, some bright and well-studied, others faint and difficult to detect. Recent surveys have continued to discover new, ultra-faint dwarf galaxies in its vicinity. This population of satellites is an important test of cosmological models, particularly those related to dark matter. Some models predict that large galaxies should be surrounded by many small dark matter clumps, some of which host stars and become visible as dwarf galaxies. The number and distribution of these satellites around the Milky Way are compared to similar systems around other galaxies to test these predictions. As the Milky Way's halo is mapped in greater detail, including faint stars and streams, it becomes possible to better understand how these satellites are distributed and how they have interacted with the main galaxy over time. This again feeds back into comparisons with other galaxies. If the Milky Way's halo is particularly rich in substructure, it may suggest a more active merger history than average. Alternatively, it may indicate that similar structures exist around other galaxies but are simply harder to detect at greater distances. In that sense, the Milky Way may not be unusual in its complexity, but it may be unusually well observed. There is also the question of scale in terms of influence. Some galaxies, particularly massive ellipticals in clusters, exert strong gravitational effects on their surroundings, shaping the motion of many nearby galaxies. The Milky Way's influence is more modest, limited largely to the local group. But within that group it plays a significant role. Its extended dark matter halo helps define the gravitational landscape that smaller galaxies move through. As estimates of the halo's size and mass are refined, the Milky Way's role within the local group can be better understood. This includes how it and Andromeda together shape the motions of more distant group members. From a broader perspective, comparing the Milky Way to other galaxies is not just about ranking it on a scale of size or mass. It is about understanding it as one example in a diverse population of systems, each shaped by its own history and environment. The realization that the Milky Way is wider, deeper, and more layered than once thought does not necessarily make it exceptional. It makes it more clearly part of a general pattern, where large galaxies grow through mergers, develop complex halos, and exist within overlapping gravitational environments. What changes is the level of detail in which this pattern can be studied. Because we are inside the Milky Way, we can observe it star by star, stream by stream, and cloud by cloud. This provides a kind of ground truth for models of galaxy formation that are applied to the distant universe. In that sense, the Milky Way is both an ordinary spiral galaxy and a special one. It is ordinary in its basic type and scale. It is special in its proximity and the level of detail it offers. As the picture of its true scale becomes more refined, its role as a reference point in the study of galaxies becomes even more important. Astronomers can use what they learn about the Milky Way's extended halo, its merger history, and its dark matter distribution to interpret observations of galaxies that are too far away to be studied in such detail. This creates a kind of bridge between the local and the cosmic. The Milky Way becomes a lens through which the broader population of galaxies can be better understood, and at the same time, comparisons with other galaxies help put the Milky Way in context, preventing it from being seen as either uniquely special or entirely unremarkable. It occupies a place in a wide spectrum of galactic forms, shaped by its own particular history, but governed by the same physical processes that operate across the universe. As new observations continue to expand the known reach of our galaxy, this interplay between the local and the distant is likely to deepen. Each refinement in our understanding of the Milky Way feeds into models of how galaxies form, grow, and interact. Each new comparison with other systems helps clarify what is typical and what is distinctive. In that ongoing exchange, the Milky Way's newly appreciated scale becomes not just a fact about our own cosmic home, but a piece of a much larger story about how structure emerges in the universe, one galaxy at a time. Beyond the reach of even the most advanced telescopes, there remains a layer of the Milky Way that is defined not by what is visible, but by what is inferred. This unseen side of the galaxy is not a small or trivial addition to the picture. In many ways, it makes up most of what the galaxy actually is. When people imagine the Milky Way, they tend to think of stars, bright points of light, glowing clouds of gas, dark lanes of dust. These are the features that shape the familiar image of a spiral galaxy. But all of these visible components together account for only a fraction of the galaxy's total mass. The majority of the Milky Way is invisible. This invisible component is known as dark matter, and it forms a vast halo that surrounds and permeates the galaxy. It does not emit light. It does not absorb light. It does not reflect light. Its presence is detected only through its gravitational effects on the things we can see. Stars orbit the center of the galaxy faster than they should if only the visible matter were present. Satellite galaxies move along paths that suggest they are being held by a much stronger gravitational field than the stars and gas alone could provide. Streams of stars in the halo curve and stretch in ways that reveal the shape of an unseen mass distribution. All of these clues point to a halo of dark matter that is far larger and more massive than the visible galaxy. James Webb cannot see this halo directly. No telescope can, at least not in the sense of capturing an image. But by revealing faint stars in the outskirts of the galaxy and helping trace their motions, Webb contributes to the indirect mapping of this invisible structure. Even so, the dark matter halo remains in many respects a shadow. Astronomers can estimate its size, its mass, and its general shape. But these estimates come with wide margins of uncertainty. Different models can fit the same data. Different assumptions about the nature of dark matter can lead to different conclusions about how it is distributed. Some models suggest that the halo is roughly spherical. Others indicate that it may be stretched or flattened, perhaps aligned with the disk or tilted at an angle. There are also questions about how smooth the halo is. According to many theories, dark matter should clump on small scales, forming a network of sub-halos, smaller concentrations of dark matter within the larger halo. Some of these sub-halos may host visible dwarf galaxies. Others may be completely dark, containing little or no stars at all. If these dark substructures exist, they would influence the motion of stars and gas in subtle ways, creating small distortions in streams and orbits that can be detected with careful measurement. So far, evidence for such sub-halos is indirect and incomplete. Some stellar streams show signs of having been perturbed by something unseen, possibly a dark matter clump passing nearby. But these cases are rare and difficult to interpret. This means that a large part of the Milky Way's true structure is still known only through hints and models, not through direct observation. There is also the question of the galaxy's outermost regions. As faint stars are discovered farther and farther from the centre, the apparent boundary of the Milky Way continues to move outward. But there will always be a point where stars become so sparse that it is hard to tell whether a given star truly belongs to the galaxy or is part of the intergalactic background. At these extreme distances, the gravitational pull of the Milky Way weakens, and the influence of neighbouring galaxies, especially Andromeda, becomes more significant. This creates a kind of transition zone, where the concept of inside and outside the galaxy loses its clarity. Webb can help push the detection of stars into these regions, but there are practical limits. Even with its sensitivity, there will be stars that are simply too faint or too isolated to be detected. Beyond them lies a region that may still be gravitationally connected to the Milky Way through dark matter, but that contains little or no visible matter at all. This region is, by definition, invisible in the traditional sense. Another layer of what cannot be seen lies in the early history of the galaxy. The Milky Way formed more than 13 billion years ago in the aftermath of the Big Bang, when the universe was much younger and denser. The earliest stages of its formation involved the collapse of gas and dark matter into the first small structures, which then merged and grew into larger systems. None of the direct evidence from that era remains in a form that can be observed easily. The oldest stars in the Milky Way, found mainly in the halo, carry chemical signatures of those early times. Their compositions reveal how much heavy material was present when they formed, which in turn reflects how many generations of stars had lived and died before them. But these stars are only indirect messengers. They do not show us the galaxy as it was in its infancy. They provide clues that must be interpreted through models of stellar evolution and chemical enrichment. In this sense, a large part of the Milky Way's past is also invisible, hidden not by distance or dust, but by time. There is also the matter of the interstellar medium. Between the stars lies a complex mixture of gas in different phases, from cold, dense molecular clouds to hot, diffuse plasma. Some of this gas can be detected through radio waves, some through infrared emission, some through absorption lines in the spectra of background sources. But there are regions, especially in the hot, diffuse halo, where the gas is so thin and so spread out that it is difficult to observe directly. This hot gas is thought to form a vast envelope around the galaxy, extending far beyond the visible disk. It plays an important role in the galaxy's evolution, acting as a reservoir of material that can cool and fall back into the disk, as well as a sink for energy and matter ejected by supernovae and stellar winds. Despite its importance, much of this gas remains poorly mapped. Its density, temperature and distribution are known only in broad terms, inferred from a small number of observations and models. This means that another major component of the Milky Way structure exists in a kind of observational twilight, neither fully visible nor entirely theoretical. Then there are the smallest scales. Even within regions that are well observed, there are details that remain beyond reach. In star-forming clouds, for example, the processes that determine how individual stars and planetary systems form happen on scales that are difficult to resolve, even with powerful telescopes. Webb can see into these clouds and reveal structures that were previously hidden, but there will always be finer details, smaller motions, and more subtle interactions that lie below the threshold of detection. This means that the Milky Way, at every level from its vast dark matter halo down to the formation of individual stars, contains layers of complexity that are only partially accessible. Another category of what cannot be seen involves phenomena that do not produce light in the usual sense. Gravitational waves, for example, ripple through space-time when massive objects like black holes and neutron stars merge. These waves pass through the Milky Way and through Earth, carrying information about distant and violent events. They are not detected by telescopes, but by specialized instruments that measure tiny distortions in space itself. In this way, there is a whole layer of galactic activity that exists outside the realm of electromagnetic observation. Similarly, neutrinos, nearly massless particles produced in nuclear reactions and stellar explosions, stream through the galaxy and through our bodies without leaving much trace. They carry information about processes deep inside stars and supernovae that cannot be seen directly. These forms of messengers add to the sense that the galaxy is more than what appears in images, even in the most detailed ones. They suggest that there are aspects of the Milky Way that are accessible only through entirely different kinds of observation, and that many of those methods are still in their early stages. There is also the possibility that some parts of the galaxy are hidden not just from our instruments, but from our current understanding. Dark matter itself is an example of this. We know it exists because of its gravitational effects, but we do not know what it is made of. There are many theories, involving exotic particles and new physics, but no definitive answer. If the nature of dark matter turns out to be very different from what is currently assumed, it could change how astronomers interpret the structure and scale of the Milky Way. For example, if dark matter interacts with itself or with ordinary matter in subtle ways, it could affect how the halo is shaped and how it evolves over time. These possibilities add another layer of uncertainty to the unseen side of the galaxy. There is also the question of whether there are entire populations of objects that we have not yet recognized. In the past, astronomers were surprised to discover things like pulsars, quasars, and gamma-ray bursts, phenomena that were not predicted by earlier theories. It is possible that there are classes of objects in the Milky Way that have not yet been identified, either because they are rare, faint, or emit primarily in ways that have not been thoroughly explored. Webb expands the range of what can be seen in the infrared, but it does not cover every possible window. There are still regions of the electromagnetic spectrum that are difficult to observe from space or from the ground, and there are observational techniques that are still being developed. This means that the picture of the Milky Way is likely to continue changing as new tools and methods come online. Another aspect of what cannot be seen is the future. The Milky Way structure will change over time. Stars will move, new stars will form, old stars will die, satellite galaxies will merge. The dark matter halo will evolve as well, influenced by the motions of the galaxy and its neighbours. We can model these processes and make predictions, but we cannot observe them directly, at least not on the timescales that matter for galactic evolution. This means that the galaxy we map today is only one moment in a long sequence of forms. There are past versions of the Milky Way that are lost to time, and future versions that exist only in simulations. In this sense, a large part of the galaxy is always invisible, either because it has not yet happened or because it has already passed. There is also a more philosophical layer to this idea of unseen structure. Every map, every model, every image is a representation, not the thing itself. The Milky Way as it exists in reality is a complex multi-dimensional system of matter, energy, and space-time. The Milky Way as it exists in our minds is a simplified version of that system, shaped by the limits of our senses, our instruments, and our theories. What we cannot see, in this sense, includes not just physical components like dark matter and faint gas, but also aspects of the galaxy that do not fit neatly into our current conceptual frameworks. As science advances, some of these invisible aspects become visible, either literally through new kinds of observation or figuratively through new ideas that allow old data to be interpreted in new ways. This process has happened many times in the history of astronomy. Planets were once seen as wandering stars. Galaxies were once thought to be clouds within the Milky Way. Dark matter was once an unexpected anomaly in measurements of galactic rotation. Each shift expanded the known universe and redefined what was considered visible. The Milky Way today is already far more detailed and more complex than it was in the imagination of astronomers a century ago, and yet, by most measures, a large part of it remains unseen. This is not a failure of observation so much as a reflection of scale. When a system spans hundreds of thousands of light years and includes components that do not interact with light at all, it is inevitable that some of it will lie beyond direct view. What changes over time is not the existence of this unseen side, but how much of it can be inferred, modelled, and understood. As instruments like James Webb continue to refine the visible picture, they also sharpen the contrast with what remains invisible. Each new discovery highlights not only what has been revealed, but what still lies beyond the edge of observation. This tension between the seen and the unseen is part of what drives the ongoing exploration of the galaxy. It keeps the map unfinished, the questions open, and the sense of scale flexible rather than fixed. In that way, the Milky Way remains, even in the age of advanced telescopes and detailed surveys, something more than a fully known object. It remains a system with a visible face and a hidden side, a structure that invites both measurement and imagination. And as the boundaries of what can be observed continue to shift outward, the presence of what cannot yet be seen becomes a quiet reminder that the story of our galactic home is still very much in progress. Somewhere along the path between looking up at a familiar night sky and learning about the vast layered structure that lies behind it, there is a subtle change in how place begins to feel. It is no longer just a point on a map or a coordinate in a model. It becomes a position within a story that is still being written, shaped by discoveries that continue to shift the background against which everything else is set. The Milky Way, once imagined as a simple spiral with a clear outline, now appears as something more like a deep, overlapping system of stars, gas, dust, dark matter, and motion, stretching farther and blending more gradually into its surroundings than earlier pictures suggested. Within that expanded view, the solar system does not move through a neatly defined home. It travels through a structure that is both familiar in its basic features and unfamiliar in its full extent. This shift in understanding changes the way inside is defined. When the galaxy was thought of as a disk with a modest halo, being inside it felt straightforward. You were either in the disk, in the halo, or beyond the galaxy altogether. As the halo grows in scale and complexity, and as its boundaries become more diffuse, that clarity softens. The solar system sits well within the stellar disk, far from the most distant halo stars and far from the faint extended reaches of the dark matter envelope. But the influence of that envelope still shapes the path of the Sun and its planets, even if it cannot be seen directly. In this sense, being inside the Milky Way now means being part of a structure whose defining features extend far beyond what is visible and whose true outline is drawn as much by gravity and history as by light. This expanded picture also reframes how the galaxy's centre is understood. For a long time, the galactic centre was a point of reference, a place from which distances and motions were measured. It was the anchor of the map. As more is learned about the bar-shaped structure in the inner regions, the distribution of stars around it, and the complex flows of gas that move through it, that anchor begins to look less like a fixed hub and more like a dynamic region in its own right. The solar system's relationship to this centre is not just a matter of how far away it is a matter of how the entire galaxy's mass, including its unseen components, shapes the Sun's orbit and the broader gravitational environment. Understanding this relationship requires thinking about the galaxy as a whole, not just as a collection of bright features. There is also a temporal aspect to this sense of place. The Milky Way that exists now is not the same Milky Way that existed when the Sun formed more than 4.5 billion years ago. The galaxy has grown, merged and changed over that time. The solar system's birthplace was likely a region of the disk that had already been enriched by earlier generations of stars, but that region itself may have moved, warped, and shifted as the galaxy evolved. In this context, the idea of a fixed home address in the galaxy becomes less precise. The solar system's location is not just a point in space, it is a point along a path, part of a long journey through a changing structure. As the understanding of the Milky Way's scale expands, that journey appears to take place within a much larger and more varied environment than once assumed. There are regions of the halo that may have been entirely absent or very different when the Sun formed. There are streams of stars from past mergers that did not exist yet, because the mergers had not happened. There are satellite galaxies that have since been absorbed, contributing material and stars to the Milky Way's outskirts. All of this means that the galaxy the solar system moves through today is, in some ways, a more extended and more complex system than the one it began in. This historical dimension adds depth to the idea of inside. It suggests that being part of the Milky Way is not just a static condition, but a role in an evolving structure. The galaxy is not a container that holds the solar system in a fixed shape. It is a system that both shapes and is shaped by the movement of its parts. Another way this expanding understanding affects the sense of place is through comparison. When the Milky Way is seen alongside other galaxies, especially those at different stages of development, it becomes clear that its current form is just one point along a spectrum of possible structures. Some galaxies are compact and dense, others are extended and diffuse, some are actively forming stars, others are largely quiet. The Milky Way's newly appreciated scale and complexity place it within a category of large, mature spiral galaxies with rich merger histories and extended halos. This comparison can make the solar system's position feel both ordinary and specific. Ordinary because it resides in a galaxy that follows the same broad rules and processes as countless others. Specific because the details of the Milky Way's history, its particular pattern of mergers, and its current structure are unique. In that sense, our place is both a common type of location in the universe and a one-of-a-kind environment shaped by a particular cosmic past. There is also a shift in how boundaries are perceived. In everyday life, boundaries are clear. A room ends at a wall. A country ends at a border. A planet ends at an atmosphere. The Milky Way does not have such clean divisions. Its stellar populations thin out gradually. Its dark matter halo extends invisibly. Its gravitational influence overlaps with that of other galaxies. Being inside the galaxy, therefore, means being part of a region that fades into something larger, rather than ending abruptly. This has implications for how the universe is conceptualized. Instead of thinking in terms of separate, isolated objects, the picture becomes one of overlapping systems, each embedded in a larger context. The solar system is embedded in the Milky Way. The Milky Way is embedded in the local group. The local group is embedded in a filament of galaxies. That filament is part of a vast cosmic web. Each level does not end cleanly. It blends into the next. This layered embedding can change the emotional tone of how place is experienced. Rather than feeling like a small point in a set of nested boxes, it can feel like a point in a continuous structure that stretches outward in all directions. This perspective does not diminish the importance of local scales. The Earth, the solar system, and the immediate stellar neighbourhood remain the environments that matter most for daily experience and for the conditions that allow life to exist. But it does place those local environments within a much broader and more connected framework. There is also an effect on how the future is imagined. As the Milky Way's structure and scale become clearer, so does its long-term trajectory. The eventual merger with Andromeda is not just a speculative event, it is a consequence of the gravitational landscape in which both galaxies exist. Understanding the size and mass of the Milky Way's halo, and how it interacts with Andromeda's halo, helps refine models of how that future merger will unfold. From the solar system's perspective, this means that inside the Milky Way is a temporary condition, in the sense that the galaxy itself will eventually become part of a larger system. The solar system will not leave the galaxy, but the galaxy will change around it, absorbing another large system and becoming something new. This long-term view adds another layer to the idea of place. It suggests that even the larger structures humans meaningfully talk about are not permanent. They evolve, combine, and transform. The Milky Way's expanding scale, therefore, is not just a matter of adding more stars or more dark matter to the map. It is a sign of a system that is still in the process of becoming something else. There is also a connection between this expanding understanding and the way knowledge itself is experienced. As observations grow more detailed, the Milky Way becomes less like a solved puzzle and more like an open field of study. Each new layer of structure revealed, whether it is a faint halo stream, a distant star cluster, or a refined model of the dark matter distribution, adds to the sense that the galaxy is deeper and more intricate than previously thought. This can create a kind of intellectual humility. The idea that even our own galaxy, the one we inhabit, is not fully mapped or fully understood, highlights the limits of human knowledge in a tangible way. At the same time, it emphasizes the capacity for that knowledge to grow. The expanding understanding of the Milky Way scale is the result of generations of observation, theory, and technological development. It is a reminder that the picture of the universe available to any one era is not final, but part of a longer process. This process also affects how the night sky is perceived. To the naked eye, the stars appear as a pattern of points on a dark background. The Milky Way appears as a soft, glowing band. With the added context of a deep, layered galaxy, those points and that band take on additional meaning. Each star becomes a marker of a much larger structure. Each dark patch hints at dust and gas. Each faint region suggests an extended halo or a distant stream. The sky becomes not just a visual scene, but a map of a complex system that extends far beyond what can be seen directly. This does not require constant awareness to be meaningful. It can sit quietly in the background, a layer of understanding that does not change what is seen, but changes what is known about what is seen. There is also a social dimension to this expanding understanding. The story of the Milky Way is not written by a single person or a single group. It is the product of a global scientific community spanning cultures, languages, and generations. As new data from instruments like James Webb becomes available, it is analysed, debated, and interpreted by researchers around the world. This collective effort shapes the evolving picture of the galaxy. In that sense, our place inside an expanding understanding is not just a physical position in space. It is also a position within a human network of inquiry. The knowledge of the galaxy is something that is built, shared, and refined through collaboration. This adds another layer to the idea of belonging. The solar system belongs to the Milky Way in a physical sense. Humans belong to a global effort to understand that galaxy in an intellectual sense. Both forms of belonging are part of the same story, one that connects local experience to cosmic scale. Another way this expanding understanding influences perspective is through the idea of rarity and commonality. For a long time, it was unclear how typical a galaxy like the Milky Way was. As surveys of other galaxies have improved, it has become clear that large spiral galaxies with extended halos and complex merger histories are not unusual. They are a common outcome of cosmic evolution. This suggests that the environment in which the solar system exists is not a rare or exotic one, at least in broad terms. At the same time, the specific details of the Milky Way's history, the timing and nature of its mergers, the distribution of its dark matter, and the pattern of its star formation are unique. This combination of generality and specificity is part of what gives the sense of place its texture. The solar system exists in a galaxy that follows common rules, but that galaxy has a particular story. As that story becomes more detailed, the sense of place becomes more grounded in a narrative rather than just in a set of measurements. There is also an implication for how the search for life elsewhere is framed. Understanding the Milky Way's structure and scale helps define the range of environments in which planetary systems exist. Some regions of the galaxy are more crowded and energetic, others are quieter and more stable. The solar system's location in a relatively calm part of the disk appears to be one of many possible places where complex life might arise. As the map of the galaxy extends and becomes more detailed, it becomes possible to identify other regions that share similar characteristics. This does not mean that life is guaranteed elsewhere, but it provides a context for thinking about where conditions might be more or less favourable. In this way, the expanding understanding of the Milky Way's scale connects to some of the most enduring questions about humanity's place in the universe, not in the sense of providing direct answers, but in the sense of defining the stage on which those questions are asked. There is also a quiet aesthetic element to this broader picture. The idea of a galaxy that fades gradually into a larger structure, that is layered and connected rather than sharply bounded, can be seen as a kind of cosmic continuity. It suggests that the universe is not a collection of separate objects, but a network of systems that blend into one another. From that perspective, inside and outside become relative terms rather than absolute categories. The solar system is inside the Milky Way, but the Milky Way is inside the local group, and the local group is inside the cosmic web. Each level is both a container and a contained. This nested structure can be a useful way of thinking about scale without reducing it to a hierarchy of importance. Each level matters in its own context. The Earth matters for human life. The solar system matters for planetary dynamics. The Milky Way matters for the long-term environment of stars and planets. The cosmic web matters for the distribution of galaxies. All of these scales coexist, and none of them fully defines the others. As the understanding of the Milky Way continues to expand, it is likely that this layered sense of place will become more prominent. The galaxy will be seen less as a single object, with a clear outline, and more as a region within a continuum of matter and energy. This does not make it less meaningful. It makes it part of a broader, more connected picture. There is also a personal aspect to this. For someone learning about the galaxy's scale, there can be a moment of disorientation, a sense that familiar ideas about distance and size no longer quite fit. This is often followed by a kind of adjustment, where the new scale becomes part of how the universe is imagined. That process of adjustment is, in a way, a small version of the larger scientific process. Both involve taking in new information, letting it challenge existing models, and then integrating it into a more complex understanding. In the context of the Milky Way, this means moving from a simple picture of a spiral galaxy to a view of a layered, evolving system with fuzzy boundaries and deep history. Our place within that system becomes less like a point on a simple map, and more like a location within a story that stretches across space and time. As that story continues to unfold, there will likely be more revisions, more extensions, and more layers added to the picture. Each of these will subtly shift how the galaxy is understood, and, by extension, how the solar system's place within it is perceived. This ongoing process does not lead toward a final, fixed answer. It leads toward a deeper, more textured sense of connection, one that links local experience to a vast, evolving structure. And within that structure, the idea of our place becomes not just a matter of where we are, but of how we understand where we are, and how that understanding grows along with the map of the galaxy itself. Eventually, attention has a way of returning home, no matter how far it has wandered. After moving through ideas of halos, dark matter, distant stars, and structures stretching hundreds of thousands of light years, awareness drifts back towards something familiar. The room you are in, the quiet sounds around you, the steady presence of the Earth beneath everything else. The sky outside has not changed. The stars look the same as they did before any of this was known. The Milky Way still appears as a soft band of light, faint or brilliant depending on where you are and how dark the night happens to be. Nothing about the view itself announces that the galaxy is larger, deeper, and more complex than earlier generations imagined, and yet the meaning of that view has shifted. Knowing that the Milky Way extends far beyond what the eye can see does not alter the pattern of stars overhead, but it does change the scale of what that pattern represents. Each visible point becomes a marker, not of an isolated object, but of a vast structure that continues well past the limits of sight. This does not require effort to hold in mind. It can sit quietly, like background knowledge, influencing perspective without demanding attention. The Earth continues its familiar motions. It rotates once every 24 hours, carrying day into night and night into day. It orbits the Sun once a year, defining seasons and cycles that have shaped life for billions of years. The Moon circles steadily, pulling tides across oceans and subtly influencing the rhythms of the planet. All of this remains unchanged by the discovery that the galaxy is larger than once thought. The Milky Way does not press closer because its scale has been revised. The halo does not suddenly reach into daily life. Dark matter does not announce itself in any tangible way, and yet, the background context has expanded. The Earth is not just a planet orbiting a star in a spiral arm. It is a planet orbiting a star that moves through a layered, extended galactic structure, one that includes faint stars far beyond the bright disk, and an invisible mass that shapes everything else. This expanded context can feel abstract at first, but it has a way of settling into something more grounded. Consider the night sky as a ceiling rather than a destination. For most of human history, the sky was a boundary. It marked the limit of reach and understanding. The stars were fixed points, distant and unreachable, symbols rather than places. Modern astronomy removed that ceiling by revealing depth, motion, and scale. The stars became suns. The Milky Way became a galaxy. The universe became vast beyond easy comprehension. Now, with the realization that even our own galaxy is larger and more diffuse than previously believed, that ceiling lifts again, just slightly, revealing another layer of distance and connection. But the lifting is gentle. There is no need to chase the expansion of scale outward indefinitely. It is enough to acknowledge that the sky above is not a flat surface, but a window into a structure that extends far beyond what the eye can follow. From the surface of the Earth, that window is always partial. Light from distant stars has travelled for years, centuries, or tens of thousands of years to arrive. The faint glow of the Milky Way carries information from regions that existed long before modern humans ever looked up. This time delay creates a kind of quiet separation. What you see is not what is happening now. It is what happened long ago, arriving just now. That fact alone can create a sense of distance that is not physical, but temporal, and yet the Earth remains firmly anchored in the present. Gravity holds everything in place. The ground supports weight. Air fills lungs. Sound travels through space at familiar speeds. The body exists at a scale where light years and dark matter halos have no immediate influence. This contrast between the vastness of the galaxy and the immediacy of life on Earth is not a contradiction. It is a layering. The Milky Way provides context. The Earth provides experience. One does not replace the other. As the understanding of the galaxy expands, it becomes easier to see how small-scale and large-scale realities coexist without interfering. The Sun's orbit around the galaxy takes hundreds of millions of years. Earth's rotation takes hours. Human thought takes seconds. Each scale operates within its own rhythm. The discovery that the Milky Way's halo stretches farther than once believed does not speed up or slow down any of these rhythms. It simply adds another layer above them. In practical terms, nothing about daily life changes. Clocks keep time, calendars still work. The night sky looks familiar, but the mental map in which all of this takes place becomes slightly larger. The Earth is not centered in the galaxy. It is not near the edge either. It occupies a middle distance, orbiting quietly in a region that has been stable enough for complex life to develop and persist. This stability exists within a galaxy that is dynamic, layered, and still evolving. That combination is not accidental. Galaxies like the Milky Way, with extended halos and long histories of gradual growth, tend to provide environments where stars can orbit for billions of years without frequent disruption. Planets can remain in stable orbits. Life has time to experiment, adapt, and endure. In that sense, the Milky Way's true scale is not just a matter of size. It is part of the reason the solar system has been able to exist as it does. The galaxy's dark matter halo, invisible and silent, plays a role in maintaining this stability. Its mass helps hold the galaxy together, smoothing out motions and shaping orbits over immense spans of time. None of this is visible from Earth, but it is present nonetheless. There is something quietly reassuring about that. Much of what supports the structure of the galaxy does so without drawing attention. Much of what shapes the long-term environment of the solar system operates on timescales far beyond human concern. This allows life on Earth to unfold without needing to respond to constant cosmic upheaval. The galaxy is active, but it is not chaotic. It has structure, but not rigidity. It changes, but slowly. This balance is part of what makes it possible to look up at the sky and feel both small and secure at the same time. As understanding deepens, the sense of being under a bigger sky does not have to feel overwhelming. It can feel spacious instead. The idea that the Milky Way extends farther than once thought does not compress human experience into insignificance. It expands the setting in which that experience occurs. There is more room around everything, more depth behind what is seen, more history layered into each point of light. From the surface of the Earth, the sky remains a familiar dome, but mentally it becomes a cross-section of something much larger, a thin slice through a vast three-dimensional structure. That structure includes regions of the galaxy that are faint, ancient, and sparsely populated. It includes streams of stars from past mergers drifting slowly through the halo. It includes an invisible mass that outweighs everything visible. All of this exists whether or not it is being thought about, and that is part of what makes the knowledge restful rather than demanding. The galaxy does not require constant attention. It does not ask to be monitored or understood all at once. It is there, moving slowly, carrying the solar system along with it. When awareness returns fully to Earth, to the quiet of a room or the darkness outside a window, the expanded understanding of the Milky Way can remain in the background, like a deep foundation beneath familiar ground. Nothing needs to be done with it. There is no action required. It is enough to let the idea settle. The Earth is small relative to the galaxy. The galaxy is large relative to the Earth. Both facts can coexist without tension. From one perspective, the solar system is a minor component of an enormous structure. From another, it is the only place where life is known to exist. Perspective determines meaning. Neither scale cancels the other. As the mind moves between these scales, there is often a moment where the sense of urgency softens. Problems that feel large on a human scale do not vanish, but they take on a different proportion. Time feels slightly less compressed. Space feels slightly less crowded. The knowledge that the galaxy moves on timescales far longer than any individual life can create a sense of continuity that is calming rather than alienating. The Milky Way existed long before Earth formed. It will continue long after current civilizations are gone. That continuity provides a kind of cosmic background stability. Within that stability, individual lives unfold, brief but meaningful. This contrast does not diminish human experience, it frames it. There is also something grounding about realizing that Earth has always been under this larger sky, even when its scale was unknown. Ancient people looked up at the Milky Way without knowing it was a galaxy. Early astronomers mapped stars without knowing their distances. Entire cultures developed stories, calendars, and philosophies based on the same sky that exists now. The difference today is not the sky itself, but the depth of understanding behind it. That depth does not replace older ways of relating to the sky. It adds another layer. The Milky Way can still be a visual presence, a source of wonder, a quiet reminder of something beyond daily concerns. Now it is also understood as a vast structure, one whose edges fade gradually rather than ending abruptly. That fading edge is important. It means there is no sharp boundary where the galaxy stops and emptiness begins. There is a transition, a thinning, a gradual blending into a larger cosmic environment. In that sense, being under the Milky Way is not like being under a roof. It is more like being within a field that extends outward in all directions, becoming less dense but never entirely absent. This idea can be allowed to drift through the mind without needing resolution. It does not ask to be visualized perfectly. It does not demand precise numbers or diagrams. It can exist as a general sense of scale, a quiet awareness that the environment surrounding Earth is larger and deeper than it appears. That awareness does not need to be held tightly. Like the galaxy itself, it can be allowed to move slowly, to settle, to fade into the background when attention turns elsewhere. The Earth remains the place where gravity feels strong, where air has weight, where surfaces support bodies. The sky remains a place of light and darkness. The Milky Way remains a presence overhead, unchanged in appearance, expanded only in understanding. As attention continues to drift back toward the immediate world, there is no need to hold on to the vastness consciously. It can remain as context rather than content. The galaxy does not require awe at every moment. It does not require constant reflection. It simply exists, and within it, the Earth continues to turn, the night continues to arrive, and the sky continues to stretch overhead, quietly containing far more than it reveals. That is enough. Nothing needs to conclude. The Milky Way does not reach an ending point, and neither does the process of understanding it. The sky above remains open, extended, and patient, and under that much bigger sky, life on Earth goes on, steady and familiar, carried gently through a galaxy that is larger than once imagined, yet no less capable of feeling like home.